Hi, and welcome again to this new series on aircraft science or aircraft, which is the part three of a sequel. I've never pictured that it would be going to this extent, but I hope that you're happy as I'm happy to present something new today. And this will cover air crash investigations, air crash analysis, how to analyze the trajectory of the aircraft, what might have happened wrong, and how to, just like a crime scene, to extract the information and dissect the victim, which is the airplane in such case, in order to recognize, in order to detect, in order to discover what exactly went wrong and led to the crash. Now, as a disclaimer, the content of this presentation is mainly informative and should not in any way or form be used as a replacement for official documents on aircraft, official guidelines, official documentation, you name it, okay? So it should be only considered as a supplement, as informative. Actually, it would cover a lot that you usually learn in such case. However, it's not a direct replacement of specific aircrafts on how to troubleshoot, how to understand or analyze what went wrong in case of emergencies or even crashes. Chapter 1, Aircraft Systems Review for Investigators. Let's start with aircraft structures. This includes the fuselage or the airframe. You have the wings and of course the moving parts of the wings, or also called control surfaces, and empennage or the landing gear and the icing boots, okay, that work by inflation and deflation, by the way. Now, aircraft structures are designed to withstand aerodynamic, inertial, which is the ram air, by the way, inertial when it comes to rotation, that bending moments, okay, the strain built up through bending due to the rotation movement, and pressurization loads due to the differential of pressure between the inner cabinet, the inner cabin rather, and the external atmosphere. Okay, and pressurization loads while minimizing weight. So we need to make a compromise between the weight of the aircraft and the structural integrity and structural robustness in order to be able for it to be able to withstand all different loads such as aerodynamic or shear loads or inertial loads or the differential of pressure due to pressurization. Investigators must understand load paths, how the load is distributed, structural redundancy, fatigue behavior, how does fatigue develop within an aircraft due to whatever reason, and finally, failure modes, how does it work? Fuselage, the fuselage provides structural integrity, okay, what keeps the entire aircraft together without falling apart or breaking apart. Payload accommodation, so how it can carry payloads, and pressurization containment, so containing pressurized air, which is the pressurized atmosphere on the inside of the cabin without allowing any leak to escape. Most modern aircraft use semi monocoque construction where loads are shared or distributed between skin frames and stringers. Pressurization stress, which is thin-walled pressure vessel approximation, okay, is given by stress of the hoop, which is the stress, I think the cross-sectional stress is given by PR divided by T, where P is the differential cabin pressure, which is the difference between the pressure of the air inside the cabin and that of the external ambient atmosphere at a specific altitude, multiplied by R, which is the fuselage radius, divided by T, which is the skin thickness. Okay, this is for the cross-sectional stress. Now, the longitudinal stress, okay, along the fuselage is given by PR divided by 2T. Again, P is differential cabin pressure, R fuselage radius, and T is the skin thickness. Now, investigators assess fatigue cracking, so where some cracks might have developed, okay, for example, in lap joints, corrosion and stress corrosion cracking, so when you have corrosion or, due to moisture and humidity within the metallic surfaces, especially the iron-made materials of the cabin, of the boats, joining the cabin together, okay, depending on the area within the aircraft that we are addressing, and explosive decompression signatures. So if there are some signatures or clues or evidence to an explosive decompression, which is when some part of the structure of the airframe breaks apart, okay, like it opens up and breaks immediately due to, again, the differential of pressure, the difference of pressure from inside and between the inside and the outside, and it had a weak point. You had a weak point within the fuselage where that air started escaping, then it bursted through that skin, okay, creating that decompression or like explosive decompression, which is a sudden decompression of the cabin. Now, just to make things a little bit clear, so let's say this is the fuselage, okay, this is the body of the aircraft, so this would be the cockpit, okay, correct. Now, the radius we're talking about is this one. And P is the differential cabin pressure, which is the difference between pressure inside and pressure on the outside of the aircraft. All right? Times radius divided by the thickness, which is the thickness of the skin or the airframe. Thickness, okay, of the structure here. That would be the thickness of the metal or whatever material that you have, separating the external of the cabin, which is the external atmosphere, and the internal pressurized atmosphere or the air where the passengers are lodging, which is in this area. Now, the stress that is longitudinal, okay, which is along the airframe, not like against the skin immediately, is given by PR divided by 2T. Again, P is differential cabin pressure, R fuselage radius, and T is the skin thickness. Wings. Wings generate lift and carry bending loads. The lift equation is given by L, which is the lift force, equal 1/2 rho V square, which is, by the way, the dynamic pressure of the moving air. It is so close to the formula of the kinetic energy, if you can notice, multiplied by S, which is the wing area, times CL, or the lift coefficient. So again, L is equal 1/2 rho. By the way, rho is the air density, 1.02 kilograms per meter cubed near sea level, times V square, which is the velocity, air velocity or velocity of the airflow, times S, the wing area, times CL, which is the lift coefficient. Now, by the way, I want to address also some factors that can affect the lift. Okay, first you have the aspect ratio, which is given for rectangular wings by B over C, and I will explain it in a moment. For general wings, it's given by B square over S. Now, for rectangular wings at first, the aspect ratio is simply, okay, so you have the airplane like this, okay, it is the ratio between B, which is the wingspan or the distance between the first tip of the first wing all the way to the second tip of the second wing, okay, the edge of the second wing. So B divided by C, which is the cross-sectional, not cross-sectional, it is the distance from the leading edge to the trailing edge, okay, which is the width of the wing, so to speak. So this is a very important metric that decides the performance of the wings of the aircraft. Now, for general wings, especially the swept ones, like for modern aircrafts, okay, you would measure it in a different way. So for modern aircrafts, the aspect ratio is given by, again, B, which is the distance between first wing and the second wing. It's also called the wingspan, by the way. Okay, divided B square, actually. For general wings, it is given by B square divided by S, which is, this time, it is the surface area of the wings. All right? So AR is given by B square. B, again, the wingspan is the distance between the first edge of the first wing to the second edge of the second wing, squared, divided by S, which is the total wings area. Now, how does the aspect ratio affect parameters like the lift, like structural integrity and robustness? Second, and third, maneuverability. Let's start with lower aspect ratio. When we talk about lower aspect ratio, it means that the wingspan, which is the distance between the two wings, is much large in relation to the width of the wing, which is C for rectangular wings, okay, and the surface, the overall surface of the wings, which is S for general wings, which would be like modern aircraft wings, such as the Boeing, Airbus, etc. Now, what is the relationship? So, when the width of the wing or the overall area in comparison to the wingspan becomes large, it means that the aircraft becomes more maneuverable, more structural integrity, so it won't turn off. Why? Because due to the footprint that is between the wing attachment and the airframe becomes much larger, okay, so it can withstand more aerodynamic loads and forces. Okay, so it becomes more maneuverable, so the lesser control you apply, it would be enough to turn the aircraft, to cause a roll movement or a yaw or, okay, etc. Or pitch up or down. That's one. Second, so again, we've spoken about the structural integrity would be much robust and it would create more lift. So it would be generating more lift. Okay? Why? Because you have a larger wing. Yeah, more air is flowing throughout the wing, you know, from the upper camber, between the upper camber and the lower camber, due to that long distance between the leading edge and the trailing edge. The difference between the curvature of the upper camber and that of the lower camber, okay, the difference in distance, in length, it would be much larger, which will create more differential pressure between, static pressure between the lower camber of the wing, which is the lower part of the wing, and the upper camber. This would create more lift, would generate more lift. So as a result, you would get more lift. However, the drag would be also increasing in such case. As for higher aspect ratio, a higher aspect ratio means that the wingspan, which is the distance between the first edge, again, of the first wing to the second edge of the second wing, or to put it simply, the overall length of both wings, adding to that the width of the airframe. Okay, so in such case, the wingspan would be much larger than the width of the wings or the overall surface. So what would be the advantage for that? In such case, you would have lesser drag. However, the disadvantage, it would be structurally more vulnerable, weaker. Why? Because you would have a higher bending loads, okay, bending moments on the wings due to the overly, like a relatively longer distance of the wings themselves. Okay, so the bending moments would be more impactful, more serious, okay? Second, concerning the footprint or like the surface of contact between the wing and the fuselage, it would be much smaller. So this would incur more weakness, okay? It would be more structurally unstable, okay? It cannot withstand the same aerodynamic loads that larger wings that have a larger surface of contact or attachment has between the wing and the fuselage. And, okay, when it comes to the lift would become a little bit weaker. Okay, so you need to depend on more powerful engines in such case. However, the advantage is less drag. So there's like a kind of equilibrium. Okay, lesser lift, however, lower drag. This would be one of the characteristics of the swept wings. An increasing aspect ratio, if I may add, you would have narrower wings, which means less maneuverability. Not only structurally, it would be weaker than a lower aspect ratio where you would have a wider wings, more attachment surface with the fuselage. Okay, so it would be structurally weaker when we're talking about a higher aspect ratio. Now, on the other hand, the lift would be compensated by the length of the wings. Okay, however, it wouldn't be at times as efficient as a lower aspect ratio airplane. Why? Because with a lower aspect ratio, the chord line, which is the distance between leading edge and trailing edge, would be increased, which in its turn would increase the overall lift. All right. As for higher aspect ratio, you would have lesser drag, but a weaker structural makeup of the aircraft while reducing maneuverability at the same time due to the smaller wing surfaces and the smaller wing control surfaces as well. Let's talk about Reynolds number, which is a very important like metric when it comes to wings. And when we're talking about laminar versus turbulent flow, we won't go very deep here. Laminar flow, it means that the streamlines of the flow of the air are like stitched together, they are close together, there's no separation, it would be more stable. Okay, turbulent flow is where you have more vortices and wakes within the airflow itself. Okay, it would no longer be stable, so to speak. Now, the Reynolds number is given by rho VL divided by mu, where rho is the fluid density, V is the velocity of the airflow, L is the length, okay, which is the length of the camber, okay, the upper camber of the wing. I think L, I'm not sure if it's the chord line. No, I think it is the length of the trajectory of the air around the wing. And mu is the dynamic viscosity. Now, notice something. When the viscosity increases, the Reynolds number decreases. Viscosity means how the molecules of the air remain stuck together, remain close to each other. Just like you would have the oil is more viscous than the water. Why? Because it remains stuck, like glued together. It flows more smoothly, more fluently in a way that is more like stable, more constant, more together without separation. Meanwhile, the water molecules break apart from each other, so the viscosity is lesser. Okay, so the viscosity is how much the molecules of a fluid are glued together. Now, with increased viscosity, you have a lower Reynolds number, but at the same time, it guarantees a more laminar flow. Why? Because the molecules of the air remain together on the same streamline. Meanwhile, for a higher Reynolds number, it means that the viscosity would be much lower. It would be small, so the airflow would be made of molecules breaking apart, separating apart. And this is, by the way, also achieved when you have a transonic or like supersonic flight. So it gets you a higher Reynolds number in such case, breaking apart the air molecules and causing a more turbulent flow. Again, turbulent flow, it means that the flow of the air is no longer laminar, it's no longer in streamlines that are stuck together and that are close to the boundary of the wing. Okay, this is when you start getting a boundary separation. Like the air is no longer curving around the boundary, it starts separating and creating vortices. Wing bending moment, simplified cantilever model. The wing bending moment M is given by WL squared divided by 2, where W is the weight of the wing, like the weight by wing area, okay? Or, so to speak, load per unit span, okay? Load, the loading, not the weight, by the way, the loading altogether with the weight, okay, per unit of span, per span unit, times L square, which is the wing semi-span, which means the length of one wing, not together. This is the semi-span squared divided by 2. Investigators, by analyzing the bending moments, can understand the overstress failures and where they started. Okay, overstress meaning due to aerodynamic loads, shear velocity of the air against the wings, flutter induced structural breakup, so the breakup of the wing due to flutter, which means severe wind forces that are shaking violently the wings, and fuel tank explosions. Let us be reminded that the reservoirs of the fuel are within the wings themselves. Empennage provides stability and control. This is horizontal and vertical stabilizers, usually at the tail. Okay, so vertical stabilizer that has the rudder, and the horizontal stabilizers that has the elevators. Okay, the moving parts are called elevators within the horizontal stabilizer. The lift force is given by Q, which is the aerodynamic pressure, or 1/2 rho v squared. This is Q actually, multiplied by S, which is the wing surface area, multiplied by CL, which is the lift coefficient. Tail plane icing or structural overload may result in loss of pitch control, which is the up-down movement controlled by the elevators within the horizontal stabilizer. BPR, or bypass ratio, which is a very important factor or parameter that I brought it up here because in the next slide we will understand why it is important. It's going to be used for something else. Okay, now the BPR, or bypass ratio, is given by the mass of the bypass air, which is the air that is, or the mass flow rate that bypasses the combustion chamber. It's not being pressurized and burned along with the fuel, divided by the mass of the core air. Core air is actually the air that is being ingested by the engine, okay, or the mass flow rate of air that passes through the compressor, combustor, and turbine. So it is the air that is actually producing the thrust in a direct way. The BPR is the ratio between both of them within, especially, talked about in jet engines also, but different kinds of engines also involved the same concept. Okay, we're gonna see. Turbofan engines used in large transport aircraft such as Boeing 737 and Airbus A320, designated by a high bypass ratio, which is the BPR that we've spoken about in the previous slide. BPR, again, is the ratio between the free stream flowing air divided, which is the flow of that air, the mass, so to speak, volumetric flow, not volumetric, the mass flow rate, okay, kilogram, how many kilogram per second per, if you want, a cavity or surface, virtual surface, crossing it through, divided by the core air, which is the air that's being pressurized on the inside of the engine, mixed by the fuel, or with the fuel, and being combusted, then exhausted while turning the turbine, which generates power for the entire aircraft. So here you have a high bypass ratio. So the mass flow rate of the free stream air is larger than the one, like the mass of the air being ingested and compressed and combusted by the engine. Thrust equation is given by T equal M, which is the mass flow rate, multiplied by velocity of the exiting air that's coming out of the exhaust of the engine, minus V0, which is the free stream velocity. Specific fuel consumption, SFC, is given by MF divided by T, or mass flow rate, M, divided by T, which is the thrust force, okay, the thrust that's being generated. Investigative focus, okay, here you have compressor stall or surge, foreign object damage, FOD. So let's say you had an object, a foreign object being ingested by the engine, such as a bird or a rock. It would damage the engine or it would block the airflow on the inside. And turbine blade fatigue. So if a turbine snaps, it would be ingested by the engine. If a turbine blade snaps due to metal fatigue and due to aerodynamic stresses, it would be ingested by the engine, disrupting the airflow and causing a backfire. Turboprop engines, common in regional aircrafts such as the ATR-72, which is a commuter plane, short range, usually used within the same country or within the same state, so to speak, like for short haul distances, not for international flights. Very fuel efficient, by the way. Okay, combined gas turbine with propeller. So the propeller thrust or momentum theory, based on the momentum theory, is given by T equal M or mass flow rate multiplied by V2 minus V1. V2 is the velocity of the air at the exhaust of the engine minus V1, which is the intake velocity. Okay, velocity of the air at the intake stage of the engine. Propeller efficiency, EPTA P, is given by T, which is the thrust times V0 or free stream velocity divided by the power of the shaft, power generated at the shaft. Piston engines used in general aviation aircraft like the Cessna 172, brake power. Okay, the power is given by 2 pi times n, which is the RPM, number of revolutions per minute, times T, which is the torque of the engine, divided by 60. It gives you the power. Common failure points would be the detonation, which means that you would get an ignition of the fuel air mixture before the cycle of compression, or like before the cycle of the compression gets to its end, which means it is supposed to happen when you get to the cycle of combustion. Okay, so when the engine is in the compression stage, it detonates, the fuel air mixture detonates, which is very damaging to the engine. Why? Because the lever would be going this way and the detonation would push it in the opposite direction. So it would be adverse to the motion orientation of the cylinder rod and the cylinder itself. Okay, second problem that would occur is fuel starvation. So lack of fuel, or the fuel is no longer getting to the engine due to a blockage. For example, one of the reasons would be icing or fuel contamination with the air. Okay, actually fuel contamination would cause a detonation. Okay, but what I mean is fuel blockage more than that. Yeah, but fuel contamination with water, for example, would cause fuel waxing during icing conditions, blocking the fuel flow to the engine and starving the engine. Okay, and finally, carburetor icing, which is the icing also leading to the icing of the fuel, so the engine would no longer work. Hydraulic, pneumatic, and electrical systems. Hydraulic systems used for landing gear, brakes, and flight controls. According to Pascal's law, you have the force being applied to a surface area, which is the piston head, for example, or the cylinder head in the hydraulics. Yeah, the surface at which the hydraulic pressure is being applied. The force for that is given by pressure times A, times the area at which the force is being applied. Hydraulic power is given by P times Q, which is pressure times the volumetric flow rate of the fluid, of the hydraulic fluid. Okay, so investigators would examine in such case fluid leaks. So has there been any leak in the fluid, contamination of the fluid itself, and actuator failure. The actuator in this case, in this context, is the piece that transforms the hydraulic motion, the hydraulic power into a mechanical power that will move what? It will move the wing surface, the wing control surface, like the rudder, the elevators, the ailerons. Yeah, these basic. The ailerons or the trims, by the way. Okay? So, hydraulics through the actuators move the ailerons, the rudders, and the elevators. The actuator, by the way, by definition, is the part that, in this context, transforms the hydraulic power into a mechanical power. Pneumatic systems. These systems provide bleed air for pressurization inside the cabin to maintain a comfortable atmosphere for passengers that has enough enrichment of oxygen, and anti-ice, which is by activating the de-icing boots, which are some sort of a rubber, inflatable rubber that would inflate and deflate continuously during icing conditions in order to break off the icing formation in order so that it would avoid the formation of ice at the wing. Because as we know already that icing conditions increase drag and degrade, or it can decay the lift capabilities of the wing by destroying its aerodynamic flow properties, okay, creating a more torrential or turbulent flow instead of a laminar flow. This would affect and destroy the lift capabilities or downgrade it to a large margin, okay, which can impose serious dangers on the aircraft. Okay, now ideal gas law, PV equal nRT, which P pressure of the air times the volume is equal to N times R, which is the gas constant, times T, which is the temperature. Okay, so investigative interest would be towards the bleed air leaks. Okay, so checking if there are some leaks in the air, for example, a crack or a leak within the de-icing boots, or for the overheat events for whatever reasons, okay, you would have a problem at the overheating level. So here, what he probably means that the system itself would overheat, okay? Because the overheating is a very large scenario, like very word with a large array of connotations. You can have overheat with anything, okay? So I believe here he means specifically the overheating with the system of the bleed air itself, okay? Or like when you don't have the gasper working on board, so the cabin would start overheating due to the lack of the airflow, or which is changing the air within the cabin. Okay, now electrical systems. So provide power for avionics. Now, for the electrical systems, they provide power for different instruments on board, navigation, different displays, the ECAM, the ECAS, and control systems as well. Electrical power is given by P equal VI, which is very important to understand why, because so that you would know how much consumption, electrical consumption is going and is needed, required by the different instruments, so that you would not be starved of that power. Okay, this is why the engine should be running all the time. Another reason, of course, it needs to fly the aircraft, but mainly the power is drawn from the engines, not the batteries. The batteries are only for backup, and many systems cannot be carried out by the battery, so they shut down during an engine emergency. Ohm's law is given by V equal IR, with I being the current and R is the resistance in ohms. Investigators analyze short circuits or electrical surges, arc tracking, so electrical arcs or like sparks due to the insulation of some wires wearing out. You would have electrical sparks between the positive and negative poles, and battery thermal runaway. So the battery would be draining out and would start overheating. Flight control systems, manual and fly-by-wire. Manual controls, okay, so here you have mechanical linkages that transmit pilot input directly from the controls to, in the cockpit, to the control surfaces. So the same force that the pilot himself applies, that same force is transmitted directly to the control surface, which would become straining when you have high aerodynamic loads against the control surfaces due to winds, due to shear velocities of stress due to inertial forces, okay, which is unlike the case in when you have a hydraulic force where the force of the pilot will be transmitted to a hydraulic pipe, okay, and then to an actuator, and the actuator would in its turn move the control, okay? Or like the fly-by-wire, also it reads the input of the pilot and the actuator would be the one moving the control surface in such case. So the control surface hinge moment is given by mh equal 1/2 rho v square, which is the dynamic pressure, by the way, or q, multiplied by s, which is the surface of the wing control, surface of the rudder, surface of the elevator, depending on the case, times c, which is the chord line, the distance from the leading edge to the trailing edge of the control, times ch, or the hinge moment coefficient. Cable failures or jammed controls are key investigative concerns, which can cripple the aircraft. Okay, and here what is required is the redundancy management. Fly-by-wire, FBW, used in aircraft such as the Airbus A320. Pilot input is not automatically, is not directly applied to the controls, but instead is converted to electrical signals. These would be processed by flight computer systems, or flight control computers more specifically. Control law, simplified feedback form, is given by UT is equal to KP, which is the control gain, multiplied by the error signal, plus KD times the difference between the error signals, or the change of the error signals during time, okay? So that would be like, describing the error from the applied input, okay, the exact, that is derived from the exact applied input of the pilot, and versus the power that needs to be applied to the control itself, okay? Because when we talk about flight computers, we're talking about the errors of analyzing the input of the pilot, okay? The errors not in the input itself, but the error of the signal that is taken from the input to be converted to an actual signal that would be applied by the actuator, which would transform the electrical signal into a mechanical signal, a mechanical action against the control surface. Investigators evaluate sensor failures, software logic, so the software itself at times would be faulty, and redundancy management. Avionics and automation includes navigation, communication, surveillance, and flight management systems, or FMS. Examples: FMS, or flight management system, the autopilot; inertial reference system, IRS; ADIRU, by the way, its name in the Boeing aircraft, which is the one that locates the position of the aircraft on the map, on the global map. So you press it in order to get the GPS current location, exact location. And once you get that, you can travel anywhere, starting from that reference point. Inertial navigation, okay, basic integration. So VT is equal integral of AT dt, which is the velocity is the sum throughout the track, okay, is the sum of all accelerations at different times, multiplied by the time span during which the aircraft had accelerated. This is from Newtonian mechanics, by the way. X of t, which is the distance traveled. Okay, so if we remove the integral, the sum symbol, distance traveled is given by the velocity multiplied by the time. Okay, so distance is equal velocity multiplied by the time. When we use the integral, so the overall distance is equal to the sum of different velocities traveled at different time spans. Summed up together, it would give you the entire trajectory, the entire track, the length of the entire journey, so to speak. Same way for the velocity, it is the sum or integral of different accelerations at different time spans. It would give you like the overall velocity. All right? Now, automation modes must be reconstructed from flight data recorders or FDRs during investigations. Aircraft performance fundamentals. Performance analysis is critical in accident reconstruction. Okay, at first, you need to assess the weight and balance. So, CG is given by sum of different weights at different points of the aircraft, okay, divided by the overall sum of weight. So this is what gives you the balancing of the weight, okay, in respect of the entire aircraft area. So WI is the weight component and XI is the arm distance, all right? So what is the arm distance? So it is the distance from the center of the fuselage all the way to that center of weight, okay? So let's say you have some weight on the wing, the weight of the engine, correct? Now, these are fixed. Usually, this weight and balance more it's concerning the undercarriage, like the different cargo that you're carrying on board. It's not for the things that are already there. But as an example, just as an example, since like we're giving examples here, let's say I'm considering the engine. Okay, so it would be the engine weight multiplied by the distance from the center of the engine, which would be the center of the gravity of the engine, the center of mass of the engine, all the way to the center of the fuselage, which is the center of the airplane. Okay, the center of the airframe of the airplane divided by, okay, the weight of this, divided here by, so it is the sum of different weights times their distance from the position of these weights all the way to the center of the aircraft divided by the overall weight of the aircraft. That would give you the balancing, whether the entire weights, the overall weights on the aircraft, are they centered and balanced or not? Is there an equilibrium or is there an asymmetric weight to one side of the aircraft, which would be dangerous in flights, by the way. Now, second parameter would be the drag equation. The drag, which is the friction against the airflow, okay, or of the airflow against the airframe, is given by 1/2 rho v squared, which is again the dynamic pressure, times S, which is the surface of the wing area, multiplied by CD, or the drag coefficient. Rate of climb, or ROC, is given by power available for the climb minus power required divided by W, which is the weight. Again, the weight is the force actually that is caused by the mass. It's not the mass in kilograms. It is the force of the mass. So it is given by mg, with m is the mass in kilograms, times g, which is the gravitational acceleration. Now the mass can be in pounds depending on whether you're using the metric system or the imperial. Second parameter here is the stall speed. Now this is very important. It is the speed at which the wings of the aircraft can no longer generate lift, okay? So this is what stall means. This is when within the aircraft you would get the stick shaker warning. It means that the aircraft is no longer being lifted up, being held by the airflow, so it would start falling. In order to recover from a stall condition, you would increase the thrust power, lower the nose in order to increase the airflow around the wings, and like surely you would come out of the stall almost immediately, depending on the altitude, depending on multiple factors, of course. Because at higher altitudes, you would have a lesser air density, so a lower lift, but also smaller drag, okay? But at the same time, you would have a weaker lift. So stall speed is given by square root of 2 times W, which is the weight of the aircraft, divided by rho SCL. Rho is the density, the air density at that altitude, multiplied by S, which is the surface of the wing, times CL, which is CL max is the maximum lift coefficient. Investigators reconstruct, in such case, the takeoff distance, climb performance, okay, and energy state at impact. If you notice something here, we see that the stall speed is inversely proportional to the air density and also to the wing surface. What does it actually mean? It means in practice that for higher altitudes, for instance, you would have a lower air density. So in return, for lower air density, you would need a higher speed to maintain the aircraft airborne. Why? Because due to the lower density of the air, so the aircraft would need to fly much faster so as to keep itself in like a leveled flight or in a climb. Otherwise, it would stall. It would lose the lift and start falling. Same thing for surfaces. So for higher surfaces, you would have more drag. So you would need like a smaller stall speeds, okay, and which means that the aircraft would need to fly faster in order to stay in the air. To make it again a little bit simple in case it was confusing. So let's say this time you're flying at lower speeds. You would have a higher density of the air, which means that the air molecules would be much closer together. The air would be heavier per volume or a volumetric unit. So which means since they are inversely proportional, when rho becomes high, the stall speed becomes low, which translates in the aircraft being capable of flying even at slow rates, even at slow speeds without stalling. So the aircraft can maintain leveled flight even at 155 knots, even for larger aircraft. Meanwhile, the difference or the opposite for that is that when the aircraft is at higher altitudes, the density would be very low, so the molecules of the air would be much further from each other. The air would be lighter, which would reflect, so for lower density, higher stall speed, which would reflect in the aircraft having to fly much faster, okay, in order to maintain its leveled flight. Why? Higher stall speeds means that instead of the aircraft stalling, losing lift at 155 knots, it can lose lift at 175, 180 knots. So you would need to be going much faster, okay, in order to avoid the stalling conditions. Now, on the other hand, there is an advantage on higher altitudes that despite the fact that the stall speed would be high, you would have less drag against the airframe. Total mechanical energy, E is equal to mgh, which is the potential energy, plus 1/2 mv squared, which is the kinetic energy. So total energy is potential energy plus kinetic. Understanding aircraft systems at both physical and operational levels allows investigators to correlate wreckage evidence, flight data from the FDR and CVR, and system behavior, CVR, by the way, cockpit voice recorder, and system behavior to determine probable cause. Module 2, Human Factors in Aviation Accidents. Human factors play a decisive role in aviation safety. Investigators must analyze cognitive abilities, physiological factors, psychological, and organizational contributors to accidents. This module integrates neuroscience, psychology, systems theory, and operational risk modeling. Let's start with human performance limitations. Human operators are subject to physiological and cognitive stress and constraints. Reaction time. Pilot response to stimuli includes perception time, which is the time by which or that it would take the pilot in order to pay attention to something, then decision time. By the way, also you can add to the perception also the factor of understanding and processing what's happening. Then decision time, which is taking decision. Actually, the processing is within the decision stage. I'm sorry, it would be more accurate to place the process or the processing of what's happening, processing of the error or the alarm in decision time. And finally, motor response time, which is the time it would take the pilot to make the correct action, okay, to actually act based on the data that he has, based on, like, this is the stage that comes right after deciding. T motor is acting, doing it, okay? So T total is time of perception when he notices a problem plus time of decision. This includes processing the alarm, understanding what it means, and taking the decision to act. And finally, time for action. During high-speed flight, even small delays increase distance that is being traveled. So the distance is equal to velocity multiplied by total time, where V is aircraft velocity and T total is total reaction time. Now, why is distance being traveled during that time of crisis significant? You see, because when it takes the pilot too much time to decide whether to get back to the runway or not, the aircraft would have traveled a little bit more, like more further from the runway. Okay, at times it comes in handy when the runway is very close and it is like in your direction, in the same direction of your flight. But in other occasions, the runway would be right behind you and you would be headed for the ocean. So you need to minimize the time, the total time it takes for you to take the corrective measure or like the action suitable in that scenario in order to, turn back to the airport, not to lose or to waste any more time than necessary before you can land. Visual limitations. Visual acuity decreases under low illumination and high workload. So when the pilot or the crew in general are stressed and too many things to do, too much workload, many tasks, the workload is actually the number of tasks that need to be simultaneously or like sequentially accomplished during a very short amount of time. Now, in such case, the signal detection performance can be modeled as D prime is equal to mu signal, which is the average power of the signal, which is actually the signal of the alert or the warning, minus the average power of the noise, okay, the average noise signal power, divided by sigma, which is the standard deviation, where D prime represents detectability in signal detection theory. Now, G-force effects, high acceleration affects cerebral perfusion, so the person can no longer focus effectively. F is equal to ma, where a is the acceleration, correct? So sustained positive G can cause G-lock or G-induced loss of consciousness, reducing pilot's effectiveness. Why? Because he can no longer focus and it impairs its cognitive and processing abilities. To situational awareness and workload. Situational awareness, or SA, consists of perception, perceiving the fault or the alarm or the indication, whatever it is, within the cockpit. Then comprehension, which is understanding what is it about and what systems are being affected based on that indication or warning. And finally, projection. Okay, so workload can be approximated conceptually as WL is equal to task demanded divided by available cognitive resources. Okay, that would be like the exact definition of workload. So it is the demand of each task divided by available cognitive resources, how much can a person process concerning that task, because you would have multiple tasks at hand, okay? Each one would require a byte from your processing capabilities. Now, if the workload is greater than 1, so if the demand is greater than the available cognitive resources, the overload occurs, increasing error probability. Information processing capacity, according to limited capacity theory, is given, okay, C used. The used capacity should be less than or equal to C max. When C used, or capacity being used, becomes closer to maximum cognitive capacity that a person has, the attentional narrowing and channelized attention occur, which means that the attention span of the person becomes more narrow. All right, channelized attention, so he would start focusing on other things while disregarding things that are even as important. So investigators examine mode confusion, the confusion that may occur due to this heavy workload, automation surprise, which means that the pilot or the crew, different crew members, can become overwhelmed by the different signals, at times conflicting signals, being generated by the flight computers and the indication systems. And loss of situational awareness, or LOC-I, which means loss of awareness on which attitude is the aircraft at the moment being in, which bankroll, which altitude, all of these different factors. Fatigue and circadian disruption. Fatigue degrades cognitive performance. Vigilance, which means the person being able to do a hard work and being vigilant, like being at his edge and pushing hard to get something out of the tasks that are being required, and reaction time. So there would be a lag between the perception of a problem and the reaction itself. Circadian rhythm approximation. Human alertness follows a sinusoidal pattern, which is given by AT, which is alertness, is equal to the average alertness plus AMP, which is the amplitude of alertness variation, times sine of 2 pi t divided by 24. 24 hours here, and t is the time in hours. Okay? So in other words, for longer hours, let's say if he had worked around 24 hours. Okay? So sine 2 pi you would get, which gives you 0. So the amplitude of alertness variation would become 0, and the alertness of a person becomes the mean alertness. So he would be crippled. He would no longer be able to become vigilant, become more attentive at the new development in the cockpit, so as to react to it properly. Performance degradation can be modeled, or decay, as performance is directly proportional to the exponential of minus kf, where f represents the accumulated fatigue. So the performance, it can decay due exponentially almost due to fatigue multiplied by k, which is a proportionality constant. Regard it as a relative constant. Okay, so as fatigue grows, the performance decays exponentially, which is very dangerous. Okay, it is serious. Investigators in such case analyze duty time, how long the pilot has been working, how many flights he had done that day. Time zone transition also affects, and it can impair the focus, and by messing up with the biological time of the pilot himself due to time zone changes. And sleep debt, being robbed from essential sleep, can impair his attentiveness and degrade his performance. CRM, or crew resource management. CRM focuses on communication between different crew members, leadership, so the pilot should be the one in charge of making decisions, while of course taking the counsel and the advice and the assistance of other crew members, such as the flight engineer, if applicable, and the first officer. Okay, so leadership, decision making, and teamwork. Teamwork is very essential, so that one would be focusing on the airspeed during emergencies and the other on flying the aircraft. Communication efficiency model, EC is equal to the ratio between correct information being transmitted, whether between the crews, among the crew members, or between the crew and the ATC, divided by the total information required in order to efficiently perform. Okay, so the reduced communication efficiency increases risks, increases coordination failure probability. And coordination failure, it means that you would have a crippled aircraft, basically, a crippled line of work. So there would be so much misunderstanding. For example, it happened before that the pilot would pull one of the levers of the engines, placing it to idle without informing the other members, okay, of the cabin, which is very important to, like, the crew members, for them to be aware of what actions have been taken. Authority gradient. Excessive authority gradient reduces subordinate challenge behavior. So the probability of intervention from any one of the crew other than the pilot himself, okay, actually intervention, it means that the pilot is flying and there should be an intervention from the first officer, for example, in order to rectify or to point to something or to bring the attention of the pilot on a very important development. So probability of the pilot being challenged is directly proportional to this fraction, or in other words, is inversely proportional to the authority gradient. As much as you give authority and power gradient to the pilot, that would decay the probability of the pilot being challenged, which is necessary, even when he's the pilot and the first officer is 20 years old, relatively new, okay? They need to work with each other, and the first officer would need to bring the attention of the pilot when something is going wrong. And the first officer would know it, like there is something not right with the procedure that's being taken. Meanwhile, the pilot might be like out of awareness on what should be done due to some stressful conditions, due to psychological conditions, or loss of focus. Okay, so this is why it is important. CRM failures often involve poor cross-checking between different member crews, cross-checking of the instruments to verify whether the indications are actually matching together, or if you have one instrument like presenting faulty values and values that do not match. Inadequate briefing. So the briefing is important so as to, like, for example, each action performed in the cockpit should be briefed, or like the other members of the cabin should be briefed on that action. Okay, like flaps 5, flaps 10, you need to voice it. You need to be vocal about each action taken during whatever stage of the flight. And finally, failure to challenge incorrect decisions. Why? Because like the first officer would think, okay, the pilot knows better than myself. Who am I to challenge him? Like, he definitely knows what he's doing because he had 20 years experience. Meanwhile, the first officer knows that this action was not proper. And for whatever reason, like the pilot fell into that, that place of error, okay? That faulty decision. Human error models, Swiss cheese model developed by James Reason. This model describes accidents as the alignment of latent and active failures through multiple defense layers. Okay, so you have one defense layer going down after the other, increasing the probability for the accident. So the probability of the accident is the sum of the different probabilities of failures that should have been avoided, okay? So you have one defense layer, one guard after the other going down, leading to a major accident or a major problem, where each P failure represents the probability of a defensive layer failing. Error types would be, okay, slips, which is the execution failures. So something that needs to be done, it was missed or overlooked somehow. Lapses, which is a failure to remember something very important or to take an action about something. That would be the memory failure or failures. Mistakes, which is planning failures. At times, like an aircraft would end in a completely different place due to an error of navigation. And finally, violations, which is wrong decisions or intentional deviations in order, for example, to shorten the flight duration when the pilot is under pressure to perform and to avoid any delays for the passengers. Investigators determine how organizational weaknesses align with frontline errors. So that would be P slips plus P lapses plus P mistakes plus P violations altogether would add up the probability for an accident. Decision making under stress. Stress affects cognitive bandwidth and risk perception. Okay, let's talk about Yerkes-Dodson law. Performance varies with arousal. So the performance is given by minus A, which is the arousal, multiplied by the difference between the stress and the optimal stress levels squared plus P max, which is the maximum achievable performance. So as the stress, as the difference of the stress decreases, okay, so if this factor is 0 and S opt is equal to S stress, this becomes 0 and the performance becomes the maximum achievable performance. So what affects or denigrates the performance is actually the stress levels. Given, by the way, the stress levels here need to be in case the stress level is negative, which is not possible, okay, you would have a positive value here. But here, S opt, okay, the optimal stress level should drop down all the way to the value of the current stress, or the current stress should be equal to the optimal stress level so as to annihilate this factor and rendering the performance as the maximum achievable performance. Now, to make something a little bit clearer, cognitive bandwidth, it means like the margin of cognition, okay? Bandwidth, just like the frequency bandwidth. When you have a larger frequency, you can modulate a larger amount of information, correct? So the cognitive bandwidth is the array that's available for cognitive abilities. When this band is large, you have more cognitive room to process info. You have more cognitive resources and abilities, okay? So stress would affect cognitive bandwidth and risk perception. Excessive stress leads to tunnel vision, which means that the person becomes focusing like this without the ability to be looking sideways for other indicators. Actually, it leads to what is called target fixation, where the pilot becomes fixated on one problem, one indication, one alert system, or one alert on a screen while disregarding other important instruments and other important readings that would be valuable to assess the situation and to correctly diagnose what's happening. Second, confirmation bias, which means that he would get an indication, it might be false, okay? However, it is confirmed by another crew member that is saying that the engine is malfunctioning. So that would be the confirmation bias, despite the fact that both the indication, the alert indication on the screen, and the other affirmation by the other crew member, both of them are false. So, but in his mind, it becomes confirmed. Why? Because he either had 1, 2 indications, both of them false, And on top of that, for example, another confirmation from another crew, like a member such as the first officer. So as a majority, they mount up to become a confirmation bias. 3, impaired working memory. So he can no longer memorize the different steps that are required in a specific situation due to stress. And the decision time under uncertainty may follow this pattern, this law. It is inversely proportional to the amount of confidence. So when you have a high confidence, the time for decision would become very low. Why? Because it is 1 over the amount of confidence. So imagine if the confidence was so high, was so stellar, almost infinity, 1 over infinity would become 0. So the time for decision becomes very swift. Investigators analyze cockpit voice recorder or CVR data for stress indicators. Organizational influences. Organizational culture and systemic factors shape frontline performance. Okay? Why? I'll tell you why. At first, let us read together. So, first, you have the Safety Culture Index, which is a conceptual model given by the risk is equal to operational pressure divided by safety controls. So, when the operational pressure increases, which means, in other words, when there is a high demand on performing, not performing when it comes to safety, performing in general. So, delivering on with short delays, delivering on short notice, being able, and this would be a pressure from the organization, from the airliner, okay, itself, a pressure placed by the airline over the pilots to reduce the delays in order to satisfy as many passengers as possible and to perform swift flights, like jumping immediately from one hole to another, from one location to another, so as to satisfy a specific requirement by the passengers, so as to keep the clients coming and being competitive, in front of other airlines. So that would lead to not only cutting corners by the pilots, but also increasing risks. So the risk is equal to operational pressure, the pressure to operate faster, swifter, push one flight after the other with minimum delay, divided by safety controls. So it would come at the expense of safety controls. Okay? If operational pressure exceeds safety margins, it becomes very dangerous, increasing risks and in a non-linear way. So, second, latent condition accumulation. So the total risk becomes the sum of different latent failures. So one failure after the other. In other words, one compromise after the other. When these compromises increase, the probabilities of different, small failures or small glitches in operations become, these probabilities become, larger and larger, leading to a risk that would be much serious, and it can actually cause an accident. Another factor of organizational culture is not only the culture of the organization or the airliner itself, but it can be the overall culture. For example, and it happened with Japanese airlines, where you had something embedded in the culture where there is so much respect between a student and a master. So when you have a co-pilot working with a pilot, you wouldn't even dare questioning some of the actions that are being performed, even when the pilot is being compromised, which means that he's under stress, he's under fatigue, he doesn't have a sound reasoning. So the pilot, the co-pilot, despite the fact that he would see some failures, some wrong operations done that can compromise the entire flight, he wouldn't dare to bring them up to the pilot due to that kind of hierarchy, which is not favorable when we're talking about an airline or a flight environment. Within the cockpit, all should be equal. Of course, the one who makes the decisions is the captain himself. However, there should be a fluent conversation and collaboration and teamwork, okay? And like there should be always transactions of back and forth concerning different items being monitored, different, like if something had was missed by the pilot, it should be brought up by the co-pilot. This is the point of having multiple crew members to begin with. Examples include inadequate training, poor maintenance oversight, also, which means that some of the things in maintenance have been overlooked or bending the catalog and the safe operational procedures, weak regulatory enforcement, and in such case or cases, investigators examine organizational policies, safety management systems, SMS, how is safety implemented in that airline, and also the history of the aircraft, historical incident patterns. Conclusion: human factors in aviation accidents represent complex interactions between physiology, cognition, teamwork, stress, and organizational systems. By combining behavioral science with quantitative modeling, investigators can identify not only active errors but also systemic vulnerabilities within the system that allowed accident trajectories to develop. And also, if I may add another example, if the pilot's health has been compromised in some way, it can, of course, affect the performance of the flight. And even when the first officer wants to take control, he can get distracted by that new development, health development on board. So this can also lead to performance errors or escalation of risks that are things developing on board. Module 3: Accident Scene Management. Accident scene management is the foundation of a successful air crash investigation. You need to have proper site control, hazard mitigation, so reduction of hazards such as potential fires due to fuel leakage, because you might have carnage, but more than that, some people may have survived. There are multiple factors. And systematic documentation ensure that physical evidence remains intact and scientifically usable, which means that the physical evidence when it comes to the debris of the airplane, all of that needs to be secured. In case of a development of a fire, it needs to be extinguished fast so that the recovery of the FDR and CVR would be made possible, along with other crucial evidence that will, partake in the investigation. Now, securing the crash site. The first priority is preservation of life, followed by preservation of evidence. Investigators must establish perimeter control, securing the site of the crash, okay, using like a yellow tape, access logs, which means not anyone can have right to access the crash site, so as to preserve evidence and make sure that nothing would be missing or stolen, and chain of custody procedures. Impact energy estimation. Understanding impact severity, how fast the airplane crashed, would help determine structural fragmentation and how far the debris is spread from the center of impact. Okay, so the energy upon impact is given by, which is, by the way, a kinetic energy. EK is equal 1/2 mv squared, where m is the mass of the aircraft, overall mass, multiplied by the velocity on impact squared. That would not be the airspeed, but the vertical plus horizontal speed upon impact. Now, you see, when the velocity would be too high, which means you would have a higher kinetic energy, it would be correlated or matched with an increased percentage of fragmentation. So the aircraft would be rendered into much smaller pieces and spread around a larger area. Okay, and vice versa. If the impact had a lower speed, which is a lower kinetic energy, the spreading would be much lesser. And the four corners of the aircraft would be sitting almost together. All right. Now, another thing to be added is that the velocity has more effect on the kinetic energy, way more than the mass, because it is being squared. Okay. While the mass, you can consider that it's being divided in half, but the velocity is being squared. Impact force approximation. F, or the impact force, is given by delta P over delta T. Delta P is the change of momentum, okay, the movement quantity, so to speak, over delta T, which is the impact duration, how long it took for the impact to, how long it was, the duration of the impact between the aircraft and the ground. Now, shorter deceleration time increases structural destruction, correct? And debris dispersion. So, if you have a shorter deceleration, which means that you suddenly fell from, like you had a very fast speed and then suddenly full stop on the ground. So you had a very fast rate between a high velocity and a low velocity, okay, it would, upon impact, it would cause a much larger structural destruction and a much higher dispersion of debris. Meanwhile, if the aircraft somehow managed to decelerate a little bit before impact, it will lessen the structural damage and also the dispersion of different fragments of the aircraft. Coordination with emergency responders. Effective coordination includes fire services, law enforcement, medical teams, and regulatory authorities such as the NTSB or National Transportation Safety Board, and also the ICAO, which is the International Civil Aviation Organization. Incident Command Structure, or ICS. This unified command ensures clear communication channels, hazard mitigation, and controlled evidence handling. Now, the communication efficiency, EC, is given by information delivered correctly divided by the information required. So that would be the ratio. The percentage or amount of information being delivered correctly divided by the total of information being required for the investigation. That would give us the efficiency of communication or communication efficiency. Breakdowns in coordination may lead to contamination. So some of the evidence or the info would be contaminated, would be like pertaining to other investigation and included in that one, or loss of evidence, which is even worse. Hazard identification. This includes fuel, because it might start fire, batteries, especially lithium, and hazardous cargo. So, for example, cargo that happens to be of military nature being transported. So that would be a hazard that needs to be dealt with before the investigation can be carried out. So it needs to be secured. Crash sites may contain residual aviation fuel, definitely. Pressurized oxygen systems, which can lead to even more massive fire. Lithium-ion batteries, and dangerous goods per ICAO technical instructions. This can be like, for example, lithium batteries of the consumer kind of, daily use, or some kind of substances that are, flammable. Fuel fire energy release. Now, energy released by fuel is given by Q equal mf times hc, with mf is the mass of the fuel and hc is the combustion heat, okay, heat of combustion or heat energy for combustion. Now, battery thermal risk. Okay, thermal energy generation rate is given by Q is equal to I square R for batteries, where I is the current that can be generated by the batteries or produced by the batteries, and R is the internal resistance. Hazard identification reduces secondary accidents and protects investigators, which is very important. Site mapping and documentation. Accurate mapping is essential for reconstructing the accident sequence. Coordinate system mapping. Positions are often recorded in Cartesian or GPS coordinates. Okay, so the distance between 2 points, by the way, is given by where x, y are like latitude and longitude if you want. So the distance traveled by the aircraft from point A to point B where the crash site is. So basically what he means here, between the point of reporting a problem when things started escalating in the airplane, okay, that GPS coordinate, that GPS point, and the point or location of the crash. The distance is given by the square root of x2 minus x1 square, which is the latitude of the first location minus latitude of the second location square, plus longitude of the first location minus longitude of the second location square. Or if we're talking about xy coordinates within like an ordinary scale, okay, that would be x2 minus x1 square plus y2 minus y1 square. The square root of those, okay, that would give you the distance measurement, which is, by the way, necessary for the breakup sequence. Photogrammetry principle using triangulation. Okay, so the distance would be, in such case, equal to the baseline multiplied by the focal length divided by the image displacement. Okay, so drone imaging and 3D laser scanning improve spatial reconstruction accuracy. The documentation includes high-resolution photography, video recordings, and sketches and scaled diagrams. To explain it a little bit further, because it might not be fairly understandable, so how does the drone measure the distance in such case? From itself all the way to the object being assessed, and basically like the length or the size of the object, or like not necessarily the size, but when it comes to the length or the width of the object, how can it assess these measurements? So let's say the drone is this one here, okay? Usually it would need to have 2 cameras at least, okay? So these are 2 cameras. And the distance between these 2 cameras is called the baseline, which is, by the way, similar to the distance between both of your eyes. That distance between 2 eyes in the head is called interocular distance, which is necessary in order for a human to perceive 3D objects, because these 3D objects would be reconstructed in your cerebral cortex. This is how we perceive 3D shapes, because we have 2 eyes. And the disparity that is created by these 2 eyes, which is, by the way, the shift of an object when you close one eye and you look at an object from the first eye, then you close the first eye and open the second one, that object shifts a specific distance. It changes position. That shift is called disparity. This is how you can perceive how far the object is. So here, let's say this drone is looking at an object, okay? So this object, based on this eye, okay, this camera, it would be in this position, but when it's shot from the second camera, it would be in that position, okay? It would shift. So the distance of shifting, which is, by the way, the image displacement, okay? This shift, by measuring that small distance, and we already know the baseline, which is the distance between 2 cameras, times the focal length, okay? So baseline times the focal length divided by the image displacement would give us the distance to that object. This is how it works. Now, the focal length is simply within the camera, the distance between the lens and like the sensor that is the receiver of the image. Okay, so this would be the focal length. One moment. Imagine like your own eye. You have basically the pupil, correct? This is the pupil, and you have on the inside like the receiver of the image, correct? Within the eye. I don't remember like what is the name of the eye of the receiver, the retina? Yeah, the retina, I think. So the distance between the pupil and the external lens basically and the retina is the focal length. Okay, that distance, direct distance. So focal length of the camera multiplied by baseline divided by image displacement would give us the distance to an object when it's shot by a drone, and this is called 3D photogrammetry. Okay, 3D, like the advantage of the 3D imagery, given that the drone itself has more than one camera. This is how it perceives distances. Wreckage distribution patterns. Debris fields reveal in flight breakup. So when the aircraft started breaking up, whether it broke up in flight, in mid-flight, or on the ground, okay, also it reveals controlled flight into certain terrains or into terrain, which is CFIT, which means that when the pilot, like for example, if he was flying during the night, unaware that he's about to run into an obstacle, this is called CFIT, which is controlled flight. It was under control, it was controlled into terrain, so he jammed into a terrain, into the floor, into a mountain. This is CFIT. Or high-speed impact. All of that can be revealed by studying the debris fields, the radius of the field, the type of wreckage, and the distance between the four corners of the airplane, the four corners being the nose, the tail, and the two wingtips. Okay? Now, ballistic debris motion. Horizontal travel distance of a debris is given by x equal vxt. By the way, this is from the Newtonian physics. Okay, so the distance is given and the size of the projectile. X is equal to vx times t. Vx being the velocity, the moment of breakup, times t, which is the time it took it to hit the floor. Okay, this would be the distance traveled. Okay, now vertical motion. The vertical motion, so when it comes to the descent, okay, the altitude, like the vertical descent, is given by y equal vyt, okay, vertical descent times time, minus 1 half gt square. Okay, so usually it's minus 1 half gt square, which is the acceleration, the vertical acceleration times square of the time, because vyt would be 0. There were no original vertical distance. This is what it means. Okay, vyt is actually the original vertical speed before the we need to add it in such case. In case the aircraft was already in descent mode, you would add this factor here. G is the gravitational acceleration. Long debris trails often indicate in-flight structural failure, which means that you had a structural breakup in mid-flight before the impact, while compact debris fields suggest near vertical impact. Energy dissipation. Okay, work done by an aircraft is equal to force multiplied by distance. Greater ground scar lengths may indicate higher forward velocity at impact, which means that the aircraft did not plunge only vertically. It was going with a high speed horizontally, so it scarred, it slashed the ground upon impact. It was still going forward. So the greater ground scar lengths will indicate higher forward velocity upon impact more than the vertical velocity. Okay, so investigators classify patterns as linear debris field. Linear, which means that when the aircraft slammed into the ground, it had a higher or relatively high forward velocity, so the scattering of the debris would be linear, just like a line. Radial distribution, which would be during impacts from a stall, so there was no forward velocity, and it was like a radius. Okay, and fragmentation zone, so you'd have different fragmentation, which means that mostly that the aircraft broke up in mid-flight way before impact. Evidence tagging and preservation. Each recovered component must be tagged with an identification number for future reference, logged with GPS coordinates so as to make the investigators capable of redrawing the entire crash site on a map and perform the measurements to see how far are different components of the aircraft or different fragments are far from each other, especially the main fragments such as the nose, parts of the wings, parts of the tail, etc. And they should be secured to prevent contamination with other objects, okay? Or like being something being carried off to another location, or being stolen, or being tampered with. The chain of custody integrity, probability of evidence contamination is given by P contamination is directly proportional to the number of uncontrolled handlings divided by the total handling controls. So uncontrolled handlings would be evidence that has been like carried away to a different location or tampered with. So this would contaminate the entire investigation. Okay, so we would prefer that the total handlings would be controlled and secured in an appropriate manner so as to prevent any contamination. Proper preservation prevents degradation of, first of all, metallurgical fracture surfaces. Why? Because when you have erosion, these fracture surfaces that carry evidence on how the aircraft broke up in the first place, these would be erased or defiled, like due or corrupted due to the erosion and due to other ambient factors. Second, electronic memory units. So electronic memory units like FDR, basically, the diagnostic chip that has been implemented lately on the airplanes, and the CVR or the cockpit voice recorder. And finally, biological evidence. Now, black boxes such as the flight data recorder and cockpit voice recorder are prioritized for recovery because they carry the data of the flight and the final conversations between the crew members. Finally, accident scene management integrates physics, hazard control, forensic science, and organizational condition. By preserving spatial relationships, mitigating risk, and maintaining evidentiary integrity, investigators establish the foundation for accurate reconstruction and determination of probable cause for the crash. Module 4. Flight data and cockpit voice recorders, or FDR and CVR. Flight recorders, commonly known as black boxes, are critical forensic tools in accident investigation. They provide objective evidence of aircraft system performance and the cockpit environment in the final phase of the flight. Function of FDR and CVR. Flight data recorder, FDR. The FDR or flight data recorder stores parametric data related to aircraft performance and system operation. Typical recorded parameters include airspeed, altitude, heading, vertical acceleration, control surface positions, so different positions of ailerons, rudder, trims, elevators, and engine parameters, which means N1 and 2 rotations, N1 being the percentage of rotation of the low pressure compressor, N2 is for the high pressure compressor, just like the RPM for turbofans, for piston jets, and oil pressure, EGT, different parameters that you see on the display of within the aircraft cockpit. Okay, so these would be crucial in order to assess and understand what happened to the aircraft during the last phase of the flight. Vertical acceleration example. So NZ is equal to L over W, and that being the load factor is equal to L, which is the lift force, divided by the weight. Okay, so in other words, this is the difference or differential between the lift and the weight. Weight is another force, by the way, which is the mass of the aircraft multiplied by the gravitational acceleration. So if we want to plot it, let's say this is the wing. So the lift force is like this. The weight is like this, okay? The weight is oriented to like downward, and the lift is an upward vertical vector. So if L over W equal 1, if the load factor is equal to 1, it means that the aircraft at that moment would be leveled. Okay, it wouldn't be climbing or descending. Now, if the lift degrades and the weight becomes much bigger, this would lead to the gradual descent of the aircraft. Let's say in such case, that would happen if the thrust has been reduced advertently, deliberately, in order for the aircraft, to prepare the aircraft for a landing, or in case of a loss of an engine, the aircraft would start going down if it cannot fly on the remaining engines. CVR or cockpit voice recorder. The CVR records cockpit audio, including crew conversations, different transactions between the crew or among the crew, radio transmissions with the ATC, auto warnings, so different buzzers and indications within the cockpit. Also ambient cockpit sounds such as the sounds of the engine, the sound of different controls being moved, or different inputs within the aircraft, or even the sounds of the computers. Okay, some things that are not voiced can be analyzed and matched later. Sound intensity is measured in decibels. So L, which is the intensity, is given by 10 log base 10 of I divided by I0. So I0 is the reference intensity, and I is the measured sound intensity, the actual intensity, divided by the reference intensity that is needed in order for the sound to be audible. Together, FDR and CVR data provide synchronized technical and human factor insight. Introduction to black box laboratories. Dedicated labs such as those operated by NTSB or National Transportation Safety Board and the Bureau d'Enquête et d'Analyse BEA, or this is the French Bureau of Inquiries and Analysis. They analyze recovered records, both of them. Okay, one is French, one is US, because the main manufacturers of aircrafts are the US and for Boeing, and France for Airbus. Now, laboratory procedures include memory board cleaning and drying, chip level data extraction, data integrity verification, and audio enhancement. Data parameters and recording durations. Modern aircraft typically record 25 plus hours of FDR data, 2 plus hours of CVR audio, which is like solid state system, okay, for solid state systems. The sampling theory for data collection when it comes to the readings of different instruments and these readings being recorded in the FDR. The sampling theory, to accurately reconstruct signals, the sampling should be greater than or equal to 2f max, the maximum frequency of the signal itself that's being measured. Okay, so Fs, by the way, this is called Nyquist criterion, where Fs is the sampling frequency and Fmax is the maximum signal frequency. Higher sampling rates, and we're going to explain how it works and what is exactly being talked about here. So higher sampling rates improve resolution, which is more accuracy of rapid parameter changes such as the stall onset. So what is the sampling frequency versus the maximum frequency of the message? Let's say you have the temperature variation having this form. This is the signal of the message, okay? The criteria being measured. So this curve here is the temperature variation. Now, this is an analog data that has an infinity of values. We cannot store all of these values within the FDR. We need to sample them, to take small samples in order to like store smaller amount of info to reduce the size being occupied by the FDR disk. Okay, so again, this is here like the temperature. Now, the sampler, this is the sampler here. The sampler would be like a square signal, okay? Or it's called the Pain de Dirac, or Dirac impulsions, okay? So this would be multiplied by the signal that we are collecting from the temperature sensor. So basically, this is how it works. I'm gonna focus on this part here because here it would be blocked from your eyes. You have a train of alternations of 1 and 0, correct? 1 and 0 values. So when you multiply 1 by the value of the heat signal, it would give you the heat signal. When you multiply by 0, it would cut it. Like it is a clipper, okay? So it would only take specific values when it's multiplied by 1, you see here. Okay, so this is the value, then you go back down. Basically, what's happening is that we are taking small chunks of the main signal. Okay, let me plot it up here. So wherever the signal is multiplied by 1, it is chunking that signal, okay, taking small parts. Then after sampling, you have quantization. Quantization means that only a mid value is taken from each chunk, and that value then should be coded by zeros and 1 by a binary code, okay? So let's say you would have a scale here. So for each amplitude value, you would have a specific code. So we're only taking like amplitude 1, 2 within the signal, 3, 4 as an example, okay? So when the value is between 2 and 3, it should be snapped to either 2 and 3. This is why the number of samples would increase the accuracy of the signal being measured. Then after that, we code them. So let's say you have 4 values. Okay, 4 values, so 2 to the power of n, because we have binary signal, is equal to 4, then n would be 2. So you would need at least, as an example, 2 bits. So 0, 0, 0, 1, 1, 0, 1, 1. Okay? So, and this is how you store them. So this first value is 0, 0. Then the second here is 0, 1, correct? Then the third is 1, 0. The fourth is also 1, 0. And finally, the final value is 0, 0, which is here. Okay? And this is how you digitally store the different values being collected from the temperature sensor. Now, when you recover it, you would recover these different points, and you would have a reconstructor that like would draw, reconstruct the signal by drawing a curve of approximation among different samples that were taken and quantized. And this is how you reconstruct the flight data. So I hope it is clear. It is a part of the theory of communication. Now, the frequency of sampling should be at least greater than or equal to 2f max. So you notice, like here you have one cycle, here you have one cycle of measurement, okay, one cycle. The frequency is much larger. The frequency of sampling, by the way, is peak to peak, okay, is 1 over the period, which is the period is distance between peak to peak. So this frequency here is much larger than the frequency of message. Not much larger, but it is fair enough that it can recover the data, okay, it can be accurate. But let's say, for an example, not being able to locate the pen, it doesn't have a cursor within it, so I'm sorry. Let's say you have a signal like this one, and the frequency, you see how small the frequency of sampling here? Because the period is too large. So here it would take only one sample. Meanwhile, the amount of data is much larger, okay, than one. So it wouldn't be accurate. This is why Shannon theory or Nyquist criterion is very important to be taken into consideration. Data storage capacity. Data size is equal to the sampling rate, which is how many samples you're taking in 1 second, the number of samples per second. And by the way, you can say it is the same as the frequency of sampling, the sampling frequency, because the sampling frequency is by definition the number of frequency cycles, sampling cycles per second. In each sampling cycle, which is 1 and 0, because 0 does not take a sample, but 1, when it is multiplied by the signal, it picks up one sample. So you would have one symbol per cycle. So the sampling rate, let's say it is 40 hertz. This means 40 samples per second, multiplied by bits per sample. How many bits is for one sample to encode one sample, multiplied by the full duration of recording, let's say 1 hour, 3 hours, etc. Investigators verify completeness and continuity of recorded data to ensure that all crucial data has been kept and stored within the FDR, which records basically digital data. And also the CVR nowadays records the analog data digitally. Recorder recovery techniques. Recorders are engineered for survivability even under extreme conditions. So they are designed to survive high impact forces, fire exposure. They can survive up to 30 minutes of fire many times, and deep sea immersion, so they can survive corrosion and salty conditions. So the impact resistance, impact deceleration can exceed A equal delta V over delta T, okay, which is the rate of change of velocity in terms of a time span. In other words, when you have an aircraft stopping slowly, like impacting slowly on a bushy area where you have trees, you would have some larger lapse of time, okay, and the velocity would be damped down a little bit, like relatively more gradually than when you have impact against hard ground. That would be a swift change from high velocity to zero, which would exceed like many limitations of the aircraft structural composition, shredding and fragmenting the aircraft further than normal impacts on low velocities. Now, to give you an example on measuring the data size, so let's say you have the sampling rate is 40 hertz. Okay, so this is the sampling rate. Bits per sample, each sample is coded via 40 or let's say 30 bits, okay? This is a fictitious example anyway, it's not accurate. And the duration of recording, let's say it is 100 seconds, okay? So duration or D is 100 seconds. So what would be the data size being recorded? So data size is equal to 40 hertz, which is 40 samples per second, times 30 bits for each sample, times 100. So that would be 12,000 or 120,000 bits, or 120 kilobits. Crash protected memory units, such as the FDR or the memory unit within the FDR, and that within the CVR, are designed to withstand accelerations exceeding several thousand Gs, even upon very high impact. Okay, now what is needed also is the thermal protection. So the heat transfer through insulation, which is the most crucial part that would protect the inside components, is given by Q equal K A delta T over D times T, lowercase t. Okay, let us break it down. So Q, which is the heat transfer, is given by K, which is the insulation conductivity, the thermal conductivity, how much does it conduct heat. Even when it's perfect, it would still conduct some temperature on the inside, to the inside, times A. Usually, by the way, a silicate based structure would be a very good, I'm not saying that I claim to know exactly what they use, but a silicate based insulation, it's very good in insulating the external from the internal. Times A, which is the surface area being exposed to the fire, times delta T, which is the differential of temperature between the outside, where you have fire, and the inside of the black box, divided by D, very important, which is the thickness of the insulation, multiplied by T. T is the time of exposure to the fire. Specialized recovery teams retrieve recorders from wreckage, water, or deep ocean environments. Data decoding and synchronization. Once recovered, memory modules are transported to accredited laboratories in order to recover the data. Time synchronization, which is very important because we need to align FDR and CVR timelines so as to correlate between the conversation within the cockpit and different aural sounds, aural indications and alerts, and also the technical inputs, the technical behavior of the aircraft, the inputs, the instruments, the readings, the pitch, the attitude of the aircraft, the altitude, different measurements. Also the airspeed and the inputs on the control together so as to form a complete picture over what had happened before the crash. Now, delta T, which is the differential of timeline between CVR and FDR, is equal to timeline of CVR minus timeline of the FDR. Signal filtering. Noise reduction may involve digital filtering, which means that according to this formula, Y of n is equal to sigma bk x times n minus k, which is, by the way, the convolutional product. And this is actually the comparison of a delayed version of the signal with the signal itself. And this averaging would remove like the drastic spikes of the signal that are actually the noise signatures within the signal itself. So a way of filtering and cleansing the signal is this delayed averaging between the current version of the signal and the signal itself, multiplied by bk, where x of n is the input signal, bk is the filter coefficient, and different bk's are coefficients as a sum. Y of n is the filtered output, which is the convolutional product of bk times xn minus k, or in other words, the filter coefficients multiplied by the shifted signal of xn, which is shifted by k from its original time travel. Investigators reconstruct aircraft trajectory, engine performance trends, and control inputs. These different factors are traced and reconstructed. Trajectory reconstruction example. So x of t, which is the overall distance being traveled horizontally, is equal to the integral or the sum of different velocities during the spans of time where these velocities were traveled by the aircraft. So dxt times t and integrated, summed up throughout the trajectory. H of t, which is like the overall altitude being lost during or prior to the crash, is given by integral VZT, which is velocities, different velocities, multiplied by the time segments. But here we're talking about the vertical descent speed. Underwater locator beacons, or ULBs. Flight recorders are equipped with underwater locator beacons that emit acoustic pulses when they are submerged, which are necessary in order to locate these like different boxes such as FDR and CVR, basically the most important ones. So the acoustic signal propagation, which is the measurement by which we can estimate where the signal is coming from and where these black boxes are located at a specific sea level or sea depth. The sound travel distance underwater is equal to D equals C times T, where C is the speed of sound in water, approximately 1,500 meters per second. And T, of course, the time it takes for the signal to travel all that distance. In order to acquire where the beacon that is attached to the FDR or CVR is located at the bottom of the ocean or the sea, we need to use the signal attenuation concept, which is described by the following formula, where the intensity of the signal being received by the ship that is searching for the black boxes is I equal to I0, which is the signal strength or signal intensity of the black box right after it comes out of the black box. Like it's being detected, when it's being detected, right next to the black box, before traveling any distance within water, multiplied by the exponential of minus alpha x, where alpha is the attenuation coefficient within seawater, of course, salty water, and x being the distance traveled, that is like both the vertical and horizontal distance. In other words, that would be the diagonal distance. Now, ULBs typically transmit for approximately 30 days. So you have 30 days before you run out of batteries, aiding underwater search operations. Now, let us represent how we can localize where the black box is sitting at the bottom of the sea. So you have the black box here, let's say, and this is the homing beacon, the ULB, and this is the ship, okay, with the detector here. So X would be this distance. This is X, okay? Now, remember that you have the altitude H, which is like the height of the sea level, or distance from the bottom of the ship all the way to the bottom of the sea. And by that, or from these two, we can get the distance, the horizontal distance between the ship all the way to where the ULB is located. So, X square, using Pythagoras formula, X square is equal to H square plus D square. So, D is equal to the square root of X square minus H square. Okay, but how to get the X value? Okay, one moment. Yeah. How to get X from this formula? We need to insert logarithm from behind the equality and at the front of the equality. So ln I is equal to, that would be ln base E, by the way, ln of I0 E minus alpha x, which is equal to, okay, let me solve it here, ln I equal, by the way, ln A times B, let's say A is I0, so ln of a product is the sum of ln's basically. So ln I0 E minus alpha x is equal to ln I0 plus ln E minus alpha x. Okay, now E minus alpha x, so remember, minus alpha x goes down behind the ln, and ln E is equal to 1, correct? So you get ln I minus ln I0 is equal to minus alpha x times ln E. ln E is equal to 1. We factor it out. So, hence, x, the distance, is equal to ln I minus ln I0 divided by minus alpha. So, in other words, that would become ln I0 minus ln I divided by alpha. That would be the distance. Error detection. Data integrity verification may use parity checks. So the parity is equal to sigma of bits from I equal 1 to n modulo 2, okay? Or CRC, which is more effective, the cyclic redundancy check. So R of x is equal to mx modulo gx. mx is the message polynomial, gx is the generator polynomial. Black box, and I'm gonna give an example about that. Black box laboratories transform raw digital signals into synchronized engineering plots, okay, curves, audio transcripts, which is the conversation, the dialect that's being represented, that is going on between different crew members, and reconstructed flight profiles or trajectories. At times, these are fed into a simulator to plot like the shape of the aircraft or like different behaviors and attitudes of the aircraft during flight. The pitch, the rolling, climbing, descending, all of that would be plotted, okay, using a simulator at times in order to better assess what had happened with the airplane. CRC evaluation or cyclic redundancy check. Let's say you have a sequence of bits that is the message or the information to be coded and to be protected, okay, for recording in such case, or for transmission, you can say. D is equal 1101 001 011. Now, we need a polynomial generator, which is G is equal to 10011, from which we can generate the CRC code. Now, once that CRC code is generated, at like recovery or during recording, so to speak, in order to verify that the data is correct, you evaluate the CRC code or like you perform the division once again by the same polynomial generator. If you get the same CRC code, it means that the data has been correctly received. So let's start. First of all, the division is done using XOR operations. With XOR, if 2 bits were different, only then you would get 1. So it is like OR, which is an addition, except 1 XOR 1 is 0, not 1. So 0 XOR 0, 0, 0 XOR 1, 1, 1 XOR 0, 1, and these are the only possibilities where you get 1. Otherwise, 1 XOR 1 gives you back 0. Okay, so let's start the division. At first, you place D, which is the sequence of bits, which is the message to be recorded. Then G right beneath like the sequence of bits, the data message, and from the left to the right. Okay, so you placed it from the left. And we start the XOR operation. So 1 XOR 1 gives us 0, 1 XOR 0 gives us 1, 0 0 gives us 0, 1 XOR 1 0, and 0 XOR 1 is 1. Now, okay, so you need to have them the same size as the polynomial generator. So you have 1 0 0 1, and I need to insert 0 from the right, okay, or to drop 0 from the right. So then I add 1 0 0 1 1, which is the generator, and we repeat the operation. So 1 XOR 1 0, 0 XOR 0 0, 0 XOR 0 0, 1 1 0, and 0 XOR 1 1. And after that, I need to drop the remainder here, okay, because they need to be the same size as G. So 1 1 0 1 1. Then I drop the generator, and we repeat the operation. So 1 XOR 1 0, 1 XOR 0 1, 0 0 0, 1 1 0, 1 1 0. And this would be the CRC code 1 0 0 0, which is the answer of the division. Okay, so you transmit the data based on the original data block plus the CRC code, which is 1000. Now, let's say we're talking about data transmission or recording. Okay. In order to verify whether the data is correct or not, this data block should be we should repeat the same operation of dividing this data block by the generator. If you get at the reception side The same CRC code, which is 1000, it means that there was no error, okay? The data is verified. In transmission, I'm talking, okay? Now, in case it wasn't verified, you need to retransmit. In case of recording, before you record the data, you need to recheck it again, okay? You need to re-register it again. Rescribe it again on the hard drive before, as long as the CRC is not correct. Once the CRC is correct and it had passed the check, then, okay, after writing the data on the hard drive, you can go and move to the other or the next data block. This is the importance of the CRC. So we have parity check. I did not bring up parity check. The CRC is even more sophisticated in checking for errors. This is how it actually works. Pressure drop or Bernoulli's approximation. The pressure drop is given by the concept of Bernoulli that the overall pressure is always constant, which means the total pressure, okay, before a valve is equal to the total pressure after the valve. So the pressure would be transformed in one way or another, but the total pressure, whether static and dynamic, would always be a constant pressure, which means that pressure total being static pressure, which is force over area, plus dynamic pressure, which is the pressure of the flowing air or fluid in such case, given by 1/2 rho v square, is equal to P2 plus 1/2 rho v square 2, which is the pressure after the leak. Okay, so if you have a surge in the pressure, in the dynamic pressure, one way or another, okay, if you have a change in the pressure within the pipe, it means that you would have a fuel leak. If we're talking about the fuel pressure, here we're talking about hydraulics pressure. I shouldn't be mixing them up. But if you have a differential of pressure between before a piston or after, or between 2 points within a pipe, this would mean that you have a leak in hydraulic leak. Leaks may be identified by fluid residue patterns. So you would have residues around the pipes leaking out. Line rupture, so a line transmitting the hydraulic pressure, the hydraulic power would rupture, would break, and seal degradation. Hydraulic loss may lead to control surface inoperability. Why? Because it's no longer receiving an actuation power, okay? Because the actuators rely on hydraulic pressure in order to activate the mechanical motion of the different controls. Finally, flight data and cockpit voice recorders provide objective, time-resolved insight into aircraft performance and crew interaction. Through careful recovery, decoding, synchronization and restoration of data, synchronization between CVR and FDR, and laboratory analysis, investigators convert recorded parameters into a precise reconstruction of the accident sequence by plotting different variables on a graph when it comes to the FDR, and at the same time listening to the conversations in the voice recorder, bringing physics, systems engineering, and human factors together. Module 5, Wreckage and Structural Analysis. Okay, wreckage and structural analysis transform physical debris into a scientific narrative of the accident sequence. Investigators apply mechanics of materials, very important, thermodynamics when it comes to heating and dilation of material, heat due to heat exposure and deformation of the wreckage, fracture mechanics so as to detect metal fatigue, for example, and forensic metallurgy to determine whether structural failure occurred before the impact, means that in mid-flight or after the impact. Impact signatures and energy absorption. Impact analysis determines aircraft attitude, velocity or airspeed, both vertical actually, descent speed and airspeed, which is the horizontal component, and structural loading at ground contact. Kinetic energy at impact is given by EK is equal to 1/2 mv squared, where m is the aircraft mass and v is the impact velocity. Higher kinetic energy results in greater structural fragmentation. So it would result into a much larger number of debris, which becomes even smaller. Meanwhile, when you have a lower kinetic energy, lower speed at impact, the aircraft would be fractured but not completely obliterated. Energy absorption through structural deformation. Work done during the deformation of the material or the metal is given by W is equal to the sum or integral of F times X, which is the force applied times the distance from a point of matter at which the force is being applied. So for example, the force applied at the wing of the tip, how does it work, or what would be the work done against the other edge of the wing, or the part where the wing is fixed on the airframe. Okay, so the force is approximated as a constant. The work is given by force times distance. The force that is applied times the distance at which the force is applied from a specific point in space, where F would be the force of impact and D is the crush distance. So in other words, you would have, for example, a fragment that has been under the exposure of the force of impact. Okay, the distance that this fragment would travel would determine the work done on that fragment, okay, by the force of impact. Deceleration estimation is given by A is equal to V squared divided by 2D. Shorter crush distance implies higher deceleration loads, okay, and more severe structural damage. So everything would be completely destroyed to small fragments due to a much higher speed of impact, which is given by this formula. So higher velocities would imply a higher deceleration rate, so resulting in a much larger number of debris with smaller fragments. Okay, investigators analyze ground scars, which means that if the aircraft or where the aircraft had slashed the ground, okay, what are the profiles of the airframe slashing the ground? Structural compression pattern. So if the aircraft collided like that, the decompression, or the compression of the cockpit would be in the same direction of the impact. This is how you start forming a bigger picture on how the impact had taken place and at what velocity, which means what would be the kinetic energy that had been generated by the impact, and directional bending of spars and frames. To give an example here, so you have three patterns of impact at first. You have the radial pattern, and this is basically when the aircraft stalls and falls almost vertically to the ground. So the wreckage would be scattered in a radius, okay, in a radial pattern. Just like when you drop a glass of water, okay, vertically to the ground, the wreckage or like the debris and the fragments would be scattered in a form of a circle, which means that only what was available was the vertical speed, the vertical velocity, pulling the glass downward without the horizontal velocity. The second pattern of impact would be the horizontal or longitudinated pattern. And this implies that the aircraft had a horizontal velocity, usually due to the fact that it still had some engine power, okay? Not necessarily, because it could be like as a glider, but it did not make it to the runway, so it crashed like this. The point is that the wreckage, instead of being like, scattered as a circle in a circle shape, radial shape, it would be longitudinal, so it would be spread forward. And here, in such case, you would examine where the different parts of different corners of the aircraft had landed and the position of the engines. If the engines were still running at the point or at the moment of impact, they would travel a little bit forward further than the main wreckage. Okay, why? Because they still had power, they still had rotation, so they would fly a little bit further than the main wreckage itself. In case the engines had flamed out, they would remain very close to the main wreckage, to the main airframe. And finally, the third crash pattern would be the scattered pattern, where the aircraft would have different parts scattered at a much larger area, which implies that it had experienced a mid-air breakup. So it started like breaking up in mid-air. That's why the wreckage would be almost everywhere, which is a very important point here. Going back to the ground scars determine how the aircraft hit the ground and what touched the ground first based on the format or like the shape, okay? The characteristics of the cut within the ground or through the bushes, because let's say the aircraft went through the bushes before crashing on the ground, you would see a specific pattern of the cut between or like within the trees, and that would tell you more about the attitude of the aircraft prior to impact. Now, structural compression patterns. These patterns are designated by, let's say, the aircraft stalled and crashed vertically to the ground. The compression would be cross-sectional against the cockpit and the other remaining parts of the airframe. Meanwhile, if it went head first or nose first, the compression would be longitudinal. Moreover, when we talk about directional bending of spars and frames, here we can talk about, for example, the blades of the engine. So if the engines were still running upon impact, you would have denting and bending of the blades in the opposite direction of the rotation of the engine. Okay, so let's say the rotation of the blades or of the engine was like that. The bending would be in the other direction, in the other orientation. Okay, so if it was clockwise, the rotation, the bending would be anti-clockwise or vice versa. And the amount of damage would tell you how much the engine was running. Moreover, how much of sand or soil has been inhaled by the engine would tell you whether it was running full force or not. In-flight breakup indicators. In-flight breakup is indicated by widely dispersed debris and overload fracture signatures. Let's first talk about the aerodynamic load. So L is given by 1/2 rho v square SCL, which of course, by the way, Q is 1/2 rho v square, the dynamic pressure, times S, which is the surface area of the wing, times lift coefficient. Excessive dynamic pressure, Q equal 1/2 rho v square. If structural load exceeds ultimate strength, which is sigma equal my divided by I, m being the bending moment, y distance from neutral axis, and I is equal to second moment of area. Okay, so this designates the structural stress against the airframe, and it should not be exceeding the ultimate stress accepted for like based on the norms. Investigators examine tensile overload signatures, which are like the overload caused by a tensile force or a force being applied longitudinally against a matter or a component such as an iron rod. Okay, so the tensile force would be the force being applied in an elongated way to stretch it. Okay, just like when you pull on a rubber, that would be a tensile force against the rubber, because it's not a cross-sectional pressure, but it is a stress being, in the same direction of the rubber ring itself. Okay, so the same way for different control surfaces. So we need to examine for any evidence of a tensile overload force. Now, second, control surface separation, which means whether and how different controls have separated in mid-air or on the ground. So we're talking about the rudder, the elevators, the ailerons, okay, and what actually caused the separation from the control, from like the wing surfaces. So the control surfaces that are the moving parts of the wings, had they separated, and how and why. Third, flutter evidence, which means that within a shearing wind, the wind would start vibrating against a control. So this is what flutter means. It means that the control was no longer solidly fixed at its rotational axis, okay, at its convolution or moving rotative axis. So it would start fluttering or vibrating against its original position, and this flutter evidence would appear as a shear stress against the axis, for example. So you can identify that by through metallurgical studies of the different components and different objects that had broken off the aircraft and the airframe itself. Fire and explosion analysis. Determining whether fire occurred pre or post impact is critical, so as to determine whether the fire was a contributing factor to the crash itself or if it happened after the impact, which would be a completely different study or consideration. Combustion energy is given by Q equal mfhc, with mf being the mass of the fuel and hc is the heat of combustion. Explosion overpressure. Peak overpressure can be approximated, overpressure of the explosion, by P equal E divided by V, where E is the released energy of the explosion and V is the confinement volume. So as much as you have an overpressure, okay, when you have a confinement, the energy that would be released would be much higher eventually due to that pressurized environment. Investigators analyze soot patterns, which are the patterns distinctive to the direction of the fire as the fire flowed through the entire airframe or different parts of the aircraft in general. Burn through directionality, so the direction of the burns, because you would have like the largest of burns going through a specific direction, and then the burns would become a little bit milder, okay, as the fire scattered throughout the aircraft. And pressure deformation of panels, so how did the panels, the different parts of the airfoil scatter, or how they had deformed through the fire and through the pressure factor. Fire damage classification includes post-impact fire, which is after the impact, in-flight fire, that would be fire in mid-air, and it would be reported usually in to the ATC, air traffic controller, and fuel air explosion. Metallurgical examination. Metallurgical analysis, which is the analysis of metals, identifies material defects, fatigue, which is described or portrayed by cracks within the section of the iron or whatever metal we're talking about. It would be illuminated by a fluorescent material. By the way, this is how you identify fatigue within these metals in a lab environment. Corrosion and overload. Overload, it means that it broke due to an overloading, an overweight, okay, against how much it can take. Stress-strain relationship. Hooke's law, and it's called, the elastic region. Sigma is given by sigma is equal to E times epsilon, with E is the Young's modulus and epsilon is the strain, how much strain is being applied to the material or the metal, which would incur this stress. Plastic deformation occurs when sigma is greater than sigma of yielding. Plastic deformation means that you no longer can recover, or the metal can no longer recover its original form. It is deformed indefinitely, which is, by the way, the exact inverse of elastic deformation. In elastic deformation, let's say I take something, okay, and let's say this paper, okay, and I bend it like this, and then once the force is being released, it will retain its original shape. It will retain or restore its original form. This would be called elastic deformation. Meanwhile, plastic deformation is irreversible. It is attained when the stress gets to a value much larger than the yield stress that a metal can take or withstand. So, plastic deformation would be like this. You see? It can no longer retain its original shape, so it has been indefinitely deformed. Investigators assess grain structure, heat treatment condition of the metal, and corrosion pitting. Fracture surface analysis. Fractography determines failure mode and sequence. Fatigue crack growth, which is Paris law, is given by dA over dN equals C delta K to the power of M, which means that the crack growth per cycle is equal to C and M being, by the way, material constants, multiplied by delta K, which is the stress intensity factor range. How much stress is being applied to the material or the metal. So the crack growth is proportional to material constants C and M and delta K, which is the stress intensity factor. Now the stress intensity factor K is given by Y times sigma, which is the stress, square root of pi times A. A being the crack length, not the thickness of the crack, how long the crack is, okay? The length of the crack multiplied by pi, square root of both, times sigma, which is the stress, times y, which is the geometry factor. Geometry factor, because you know the stress intensity factor has to do with the geometry of the material or the metal here specifically. Failure occurs when K becomes greater than or equal to KIC, which is the fracture toughness. Now, fracture types, you have ductile overload, like shear lips, dimples. Okay, when you have a shear stress, it means that the shearing is not longitudinal, but rather it is against like the direction of the iron rod, for example. Brittle fracture like cleavage, so it would be like this. Okay, that would be brittle fracture, you see, like that, and fatigue striations. Okay, so fatigue overloading in general. Now, fatigue striations are marks produced by the original fracture that indicate the growth of the fracture. Okay, so the fracture itself would start incrementing, increasing. It would start growing up. That would be the fatigue striations. It's not the original fatigue crack itself, but it is the growth of this fatigue signature. Bird strike and foreign object damage, or FOD. Bird strikes and foreign object damage can cause structural or engine failure, definitely. The impact momentum, F, is equal to delta mv divided by delta t. Mv is the momentum or quantity of movement in French, which is mass times velocity, over delta t, which is the duration of time in which that momentum had taken place against the wings or against the engine. Okay? Bird strike kinetic energy is given, of course, by E equal 1/2 mb v square, with mb is the mass of the bird, definitely, and v square is the velocity of both the bird and the aircraft summed up together. It is the relative velocity, not only of the bird, because both of them would be moving against each other, the bird and the aircraft. Engine ingestion analysis may involve rotational energy, okay, because what had struck the engine would be also rotating within the engine, incurring more damage. So E rotation is equal to 1/2 I omega square, with I is the inertia or moment of inertia, and omega would be the angular velocity. Okay, so that would be 1/2 I omega square. Very close, by the way, to the kinetic energy in structure. This formula is. As an evidence, investigators would examine feather or biological residue. By the way, biological residue used to be detected using black light. I'm not sure if it's still used, but it was very common in order to detect the presence of blood and other organic materials through a specific glowing when or once it is exposed to the black light. Now you have another substance also, it was used later, which is the luminol. I don't know what they're using, I'm not sure what they're using today. Blade deformation patterns, which means the blade would either crack or bend due to the bird ingestion. So it would have a very unique pattern as a signature that would indicate bird impact, impacting against the engine compressor. Also, compressor damage due to that impact. So it would be like dented on the inside and it would be damaged. Actually, it would usually result into, if the bird was too large, it can lead to an engine flameout. Finally, wreckage and structural analysis integrate mechanics, materials, science, thermodynamics, and fracture mechanics to determine whether structural failure preceded impact or resulted from it, which is very important because you would have different signatures for both cases. By interpreting deformation patterns, burn signatures, whether you have like a combustion within the engine and fire within the engine, and microscopic fracture characteristics, investigators reconstruct the physical sequence of structural events leading to the accident. Module 6, Power Plant and Systems Analysis. Power plant and systems analysis determine whether propulsion or onboard systems contributed to the accident sequence, one way or another. Investigators apply thermodynamics, fluid mechanics to examine the airflow or the fuel flow within different pipes before the engine and the exhaust flow, etc. Material science and electrical engineering principles to identify the origins of failure. Engine teardown procedures. Engine teardown is performed under controlled laboratory conditions after documentation of external damage. Okay? In order to examine what's on the inside. The primary objectives is to determine rotational signatures. So if you have a denting or a bending of the blades in the opposite direction of the rotation of the engine, it would indicate that the engines were still running prior to impact. Okay? Plus, identify internal mechanical failures such as compressor damage, blade breaking off, or internal fire. Assess pre-impact versus post-impact damage. Rotational energy, which we've seen before, that would be the evidence of engine power at impact, may be inferred from rotational energy, which is E-rot is equal to 1/2 I omega square, where I is the moment of inertia and omega is the angular velocity. How many radians per second the engine was rotating. Gas turbine thermodynamic cycle or Brighton cycle. Here, okay, we can get compressor pressure ratio is given by RP, which is the ratio of compression or the differential of pressure between the pressure of the air after the compressor and that before the compressor or the compression cycle. So RP is equal to P2, pressure of the air at right after the compressor had done its job, divided by P1, which is the pressure of the air or original pressure of the air before the compressor. So P2 divided by P1. Now the thermal efficiency approximation is given by eta TH is equal to 1 minus 1 divided by RP, which is the compressor pressure ratio, to the power of gamma minus 1 divided by gamma, where gamma is the specific heat ratio. Now, investigators examine blade rub marks, if the blade had rubbed, bearing seizure, okay, so due to the load, so do we have like seizure markings, okay, and finally shaft misalignment. Turbine blade failure mechanisms. Turbine blades operate under extreme thermal and centrifugal stresses. Now, This is due to the fact that the blade is rotating around an axis, and due to the evolution motion around the center, that would generate a centrifugal force that would be acting longitudinally against the blade. So this is why it would be a tensile stress, a force acting in the same direction of the blade itself, not a shear stress, because it's not a cross-sectional stress being applied sectionally, okay, on the blade, but rather it has the tendency to stretch the blade in the same direction of the blade itself. So the centrifugal stress is given by sigma c is equal to rho r square omega square, where rho is the material density, the density of the iron or the titanium usually, okay, the same matter the blade is made of, times the square root of the radius, okay? So it has to do with the surface of the blade to a specific extent, because the surface is pi r square, multiplied, actually, no, the surface of rotation, okay, like the surface of the disk of rotation, times omega square, which is the angular velocity. Now, that would be, by the way, the radius of rotation, which means that it is the length of the blade, adding to that also half of the axis of rotation. So from the edge all the way to the center of the revolution of the blades. Thermal stress, sigma thermal, is given by E alpha delta T, where E is Young's modulus, that has to do with the type of metal that we are dealing with, times alpha, which is the thermal expansion coefficient, times delta T, which is the differential of temperature, or temperature difference between the heating and the external temperature, okay? Or like the original temperature of the blade, for instance, and the temperature it is being exposed to from the outside. Creep deformation, at high temperature, you would get creep strain rate, okay, is equal to A times, which is the area at which it is being applied, times sigma to the power of n, which is the stress, okay, times exponential of minus q divided by RT, where q is the activation energy, divided by RT, R being the gas constant, and T is the absolute temperature. The failure mechanisms include high cycle fatigue, low cycle fatigue, low cycle, which means, rotation that happens to be slow, creep rupture, okay, the rupture of the material, okay, of the creep, and foreign object impact, FOD, for example, impacting the engine and the blades. Now, creep is a metallurgic deformation that would start developing in a metal due to exposure to high temperatures. So as these high temperatures are exposed over and over, or exposing over and over the metal itself, it would start getting the creep more serious, the deformation would start growing, and eventually the entire material would rupture due to that creep, okay? And this is called creep rupture. So the metal that has been deformed due to heat, it would get to a point where it can no longer withstand the high temperature, okay? And it would start breaking off gradually, then finally it would completely collapse. It would completely rupture. Fuel contamination detection. Fuel system integrity is critical for engine reliability. So the fuel flow rate is given by MF, which is fuel flow rate in mass, is equal to rho times FQ. So rho F is the fuel density times Q, which is the volumetric flow rate, given by A times V. A being the cross-sectional area of the pipe, for example, where the fuel is flowing, times V, which is the velocity of the fuel itself. So we can rewrite this equation as MF is equal to rho density times A, cross-sectional area, times V, which is the velocity of the fuel within the pipe or within whatever environment we're talking about. Contaminants such as water or particulates alter fuel properties. Okay, so these are different elements that can get into the fuel and contaminate it. Okay, and they would alter the fuel inflammation or combustion property. They can cause, by the way, a detonation within car engine cylinders, which means that the combustion or the ignition would take place before the combustion phase within the cylinder, while like the piston the cylinder rod is still pushing the cylinder cap to compress the fuel. Okay, so even before getting to the combustion phase, the detonation is the ignition that is premature right before the combustion phase, like outside of the correct stroke of the cycle. Water separation, which is density difference. Settling velocity based on Stokes' law is given by V equal 2r squared, with r is the droplet radius of the water, times rho p minus rho f, which is particle density, minus rho f, which is the fuel density, divided by 9 mu, or dynamic viscosity, commonly known as viscosity, multiplied by g, which is the gravitational acceleration in meter per second squared. Investigators analyze fuel samples to check for water separation, filter clogging, whether the filters are clogged that are supposed to displace water from the fuel, and microbial growth. For example, the growth of fungus within the filters. To further explain the formula that we have here, V, which is the settling velocity or the velocity at which a particle of water, let's say, a contaminant or a metal or whatever you want to call it, usually we're talking about water here within the fuel, would settle at a specific velocity of flow within the fuel. That velocity V is equal to 2r squared, r being the radius of the water particle itself, multiplied by the differential of density, which is the difference of density between water and fuel, times g, or the gravitational acceleration, 9.85 meter per second square, around that, divided by 9 mu, with mu being the dynamic viscosity of the fuel itself. Module 6, Power Plant and System Analysis. Electrical failure tracing. Electrical system failures may cause loss of avionics, which are the main instruments within the aircraft, fire due to overheating or electrical surge, overheating due, for example, to overconsumption. That would be the current load being much higher than the overall load that a wire can take. So it would be withstanding much higher current than by design, than it was designed to. So that excessive current would be converted into heat, causing a fire or an electrical spark next to an inflammable material, for instance, or control issues. In Ohm's law, V equal IR or RI, which means the voltage is equal to the resistance of a component multiplied by I, which is the current. This can apply also to the wires. So the V within the wire is also subject to current times the resistance. Power dissipation is given by Ri squared, okay, which is Vi, by the way, also. So R resistance times I squared. Excessive resistance at connections can cause overheating, okay, and the higher power dissipation and arc tracking. Short circuit current, I for short circuit is equal to V divided by the total resistance. So investigators in such case inspect arc beads, insulation damage of the wires, and circuit breaker positions, whether the breakers had opened up the current or not, or had failed to, had opened up the circuit, not the current, or had failed to pop up. By the way, as a side note, arc beads or electrical arcing is the flow of the electrical current in the air, what you would call usually a sparkling. okay, an electrical surge from outside of the wire of the conductor due to a lack of insulation or a wear down of the insulation, and that arcing would be a spark that is going from the wire to a negatively charged wire, okay, a wire of an opposite polarity, or against like the airframe itself, where you would have a metal going on that would act as a negative bus bar. Hydraulic leak investigation. Hydraulic systems operate at high pressures to actuate flight controls and landing gears. Actuation, by the way, means the transference and the conversion between a mechanical hydraulic power, actually a hydraulic power, into a mechanical power that moves the controls such as the rudder, the flaps, the gears, etc. Based on Pascal's law, F, the force, is equal to the pressure being applied multiplied by A, which would be the cross-sectional area or the area of the piston where the pressure is being applied. Continuity equation is given by, which is the flow rate, okay? Q, volumetric flow rate, is equal to A times V, A being the cross-sectional area and V is the velocity of the fluid. Maintenance-induced failures. Improper maintenance can introduce latent failures. For example, bolt-torque relationship. The torque force against a bolt is given by KFD, T being the torque force, as you rotate the bolt by a specific, designated and specialized tool for that, is equal to K, which is the torque coefficient, times F, the preload force, times D, which is the bolt diameter. If you over apply pressure or torque force against the bolt, you may crack it, okay? This is why it's important to calibrate the torque wrench in a way so as to avoid over pressing it, over applying more shear stress against that bolt, okay? Now, under torque may cause joint loosening. So under torque, it means that the torque being applied was lesser than the amount needed for the bolt to be fastened correctly in place, okay? So it might loosen due to vibrations in mid-flight, and over torque may cause metal fatigue and bolt fracture, so it can fly off in mid-air, okay? It can break apart, setting a sequence of events that can lead to a serious problem. Fatigue life estimation is given by NF equals sigma A divided by sigma prime F to the power of -1 over B. Sigma A is the alternating stress, sigma prime F is the fatigue strength coefficient, and B is the fatigue exponent. Maintenance-related failures may involve incorrect part installation, improper lubrication of the part, incomplete inspections, so you might have missed something that needed to be replaced or that was damaged and got overlooked, and documentation errors. As a final conclusion, power plant and systems analysis integrates thermodynamics, structural mechanics, and fluid dynamics, and also electrical engineering to determine whether propulsion or system malfunctions contributed to the accident. Through systematic teardown, laboratory testing, and forensic evaluation, investigators distinguish between operational failure, environmental damage due to the environment, and maintenance-induced deficiencies. Module 7, Weather and Environmental Factors. Weather and environmental conditions play a critical role in aviation accidents. Investigators analyze atmospheric physics, meteorological data, so what was the weather like on the day of the accident, terrain effects, because the airflow can be affected or altered by the terrain itself, and visibility, and environmental hazards to determine their contribution to the accident sequence. So, meteorological data sources. Accident investigation relies on multiple meteorological sources such as the METAR or Meteorological Aerodrome Report, TAF, or Terminal Aerodrome Forecast, SIGMET and AirMet advisories, weather radar imagery, satellite observations, and upper air soundings, which is the radio sound. Now, as an example on how they work, for instance, weather radar imagery is based on electromagnetic waves being reflected from different layers of the atmosphere, from clouds, from precipitation. These would be visualized in order to determine, the condensation and like the thickness of different layers of clouds and, the structure basically of the atmosphere. And what kind of clouds are being transported, are being pushed by the winds, the displacements of the clouds, air water density, etc. Meanwhile, the upper air soundings basically rely on measuring the echo of sound, okay, in order to visualize like the structure, okay, the structure of the clouds within the atmosphere that's being detected by this device. Atmospheric pressure variation was altitude using the barometric formula. So P is equal to P0, which is the sea level pressure, times exponential of minus mgh divided by RT. R is the universal gas constant times T, which is the gas temperature, and M is the molar mass of the air times G, gravitational acceleration, times h, which is the current altitude. This is how the pressure is measured, and from that pressure you can get, by the way, the altitude of the aircraft at which the aircraft is. Density variation from the ideal gas law, rho, the density, it's given by P, which is the air pressure or like the pressure of the gas, whatever it is, divided by R specific, the constant of the gas, the specific gas constant, multiplied by the temperature, the current temperature. So, rho basically is proportional to the pressure. In other words, since the lift of the wings is actually generated by the differential of pressure between the lower camber, okay, the static pressure at the lower camber or the lower part of the wing, and that of the upper camber, which is like the upper side or area or skin of the wing, that differential of pressure is the factor that creates lift. So, since the pressure is subject to density, as density decreases, that differential of pressure also decreases, which can also deteriorate lift at high altitudes. So the lift itself is subject to difference of pressure, hence it is subject to density. So air density directly affects lift and also engine performance, since the starvation of oxygen is due to a lower density at higher altitude. So both items or both parameters would be affected. Not only the lift factor, but also the thrust itself, since the combustion would be consuming more fuel while generating less thrust at times. The thrust itself wouldn't be as effective as we hope so. Thunderstorms and microbursts. Thunderstorms contain hazards such as lightning, which can electrify the aircraft and ignite the fuel within the wings, hail that can inflict structural damage against the airframe, especially the windshield, and damaging the blades of the engine through ingestion, severe turbulence that can topple or turn the aircraft, causing a rolling motion, and finally microbursts, which are sudden downdrafts of the cold air that can represent as a headwind at first, but then they push the aircraft suddenly downwards to the ground in case they were not immediately dealt with. The microburst downdraft velocity is given by V. Okay, so vertical acceleration is A equal delta V divided by delta T, which is the rate of change of velocity in terms of time. Rapid downdrafts reduce aircraft lift. So L lift is equal to dynamic pressure again, which is 1/2 rho V squared, times S, which is the wing surface, times lift coefficient or CL. If sudden headwind loss occurs, airspeed decreases immediately, reducing lift and potentially leading to a stall. This is what usually happens with the microburst in case it wasn't prematurely or preemptively dealt with. Convective or convective energy cape is equal to integral of LFC, which is the level of free convection, to EL, equilibrium level, G times T parcel minus T environment, okay, temperature of the parcel minus temperature of the environment, divided by the temperature of the environment times dz, okay? So higher Cape values indicate stronger convective storms. This is to detect whether the microburst exists or if there's a potential microburst or not. Wind shear and turbulence. Wind shear refers to rapid changes in wind speed or direction over short distances. The shear gradient is given by delta V over delta H, which is the change rate or like the change of velocity in terms of change of altitude, sudden change of velocity in respect of change of altitude. So if there's a sudden or a vast change in a shorter altitude, that would give you a higher shear. Load factor during wind gusts is given by delta N equal rho, which is of course air density, times V, velocity of the air, times A, which is the lift curve slope, times U, or gust velocity, divided by 2W over S, which is the wing loading. Severe turbulence can exceed the normal loading that can be withstood by the wings, okay? It can exceed structural load limits because it would increase the loading on the wings and even the entire airframe in such case. Icing and contamination. Icing alters airfoil shape and reduces the aerodynamic performance by degrading lift and increasing drag. Lift reduction due to ice, so the modified lift equation that is caused by the icing becomes L equal 1/2 rho V squared times S times CL iced. Now the lift coefficient would be the factor that would change due to the change of the shape of the wing incurred or caused by the icing. So CL for the iced wing is less than the lift coefficient for a clean wing. Stall speed increase. One of the signatures of icing on the wings is the increase in stall speed, which means that normally the aircraft that usually stalls at lower airspeeds would even start stalling at higher airspeeds due to icing formations on the wings. So Vs is given by square root of 2W, which is the weight of the aircraft, divided by rho SCL max, where rho is the density, S is the wing surface area, and CL max is the lift coefficient due to icing. You see, SCL, which is the lift coefficient, decreases, the stall speed increases because they are inversely proportional. So CL max, which decreases due to icing, causes higher stalling speed. Ice accretion rate, M ice, which is the mass of ice being accumulated, is given by EC, or collection efficiency of the ice on the wing, times rho W, which is water density, multiplied by V, velocity, times A, or impingement area, area of accumulation of the ice. Or in other words, the area that's being exposed to the flow of precipitation plus ice, okay? The flow of iced water or iced particles. Investigators analyzed the icing system functionality, whether it was working before the accident or not, residual contamination, whether is there still some residuals from the contamination itself, and meteorological conditions, what was the weather like on the day of the accident. Volcanic ash encounters. Volcanic ash contains abrasive silicate particles that can damage the engines and airframes. And it happened in the past, by the way, where an aircraft that was heading to Heathrow Airport, I think, got scraped by a volcanic eruption. Okay? Particle kinetic energy is given by E equal 1/2 mPv squared, where mp is the particle mass. High temperature turbine sections may melt ash particles leading to glass-like deposits. The engine temperature rise due to blockage caused by ash is delta T is equal to Q divided by MCP. So the ash blockage may reduce the airflow within the engine and increase exhaust gas temperature or EGT. Okay, investigators examine compressor erosion on the inside of the engine, turbine deposits, which is the residues of the ashes and the glass-like components that get pushed all the way to the rear end of the engine that had melted and then solidified again. And finally, air data sensor blockage. Terrain and obstacle considerations, or CFIT here. Okay, the term CFIT, which means or stands for controlled flight into terrain, or CFIT, occurs when an airworthy aircraft under pilot control, so it had some controllability, so it was under control but still collided with terrain due to the fact that, lack of visibility, or the pilot got distracted or whatever reason, but it was under control. It wasn't like the pilot, for some reason, like hydraulic pressure failure or hydraulic fluid leak, lost the control of the aircraft, and that's why it jammed into a mountain or a terrain. No, it was a controlled flight into the terrain. The minimum safe altitude, and by the way, it has to do a lot and more often with visibility. So the minimum safe altitude MSA is given by elevation, which is the highest obstacle in the land, plus clearance, which is an additive margin of altitude that should be respected by the pilot in order to make the aircraft, higher enough from the highest obstacle. Okay, so in case he had some problem, he can still have some room to recover without plowing into the terrain or a high object within the terrain. Climb gradient requirement, which you can also call climb rate. This is how much amount of altitude the aircraft is gaining in respect of distance, horizontal distance being traveled. So let's say it gained 5 meters or 10 meters after traveling 3 meters. That would be 10 divided by 3, which is 3.333 meters. Okay, that would be the rate. So required climb performance, ROC, or required climb performance, is given by available power minus power required to make the climb divided by W. Okay, divided by the weight. Okay, where ROC is the rate of climb. The impact energy with terrain is given by total energy equal mgh, which is the potential energy. It has to do with the altitude of the aircraft from the ground times the mass or the weight of the aircraft, which is mass times gravitational acceleration, plus the kinetic energy. And by the way, at a specific height, you have the kinetic energy, which is due to the motion of the aircraft, plus the altitude. Now, upon impact, all of that potential energy transforms completely into a kinetic energy. Adding to that, the velocity, the original velocity by which the aircraft was traveling. So, investigators, by the way, kinetic energy again is 1/2 mv squared. Investigators analyze terrain proximity warnings, TAWS, okay, proximity alert systems on board, like which would start alerting the crew that they're about to approach the terrain by a call, an oral signal that starts saying, terrain, okay, oral indication. Altimeter settings, so whether the altimeter is working properly or not, and it should have been adjusted in a way to measure the differential pressure, okay, between current altitude and the reference altitude, not sea level necessarily, by the way, because you might be landing on a high ground, okay, on a higher terrain or a higher runway that is above sea level already. And visibility conditions that should be clear. Okay, you have what is called aeronautical decision, which is the height at which you need to decide whether you can move forward if the runway had become visible to you, or you need to perform a toga or turn over and go around to make another attempt at the airport, at the runway, to land the aircraft. Finally, obstacle clearance procedures. So you need to be cleared of all obstacles such as the ILS poles and other ambient obstacles, ambient objects. As the final conclusion for this module, weather and environmental factors combine atmospheric physics, aerodynamics, and terrain interactions to influence aircraft performance and safety, due to the fact that the weather can affect visibility and the terrain would not be, clear in front of the pilots. By reconstructing meteorological conditions and whether there was a volcanic eruption or not, and environmental constraints, investigators determine whether atmospheric phenomena or terrain proximity contributed directly or indirectly to the accident sequence. Module 8, Flight Operations and ATC Investigation. Flight Operations and ATC, or Air Traffic Control Investigation, examines operational decision-making, regulatory compliance, whether everything was made and every decision was correct, okay, in a proper way, trajectory reconstruction of the aircraft, and coordination between flight crews and controllers. So let's say the aircraft disappeared. Based on radar tracking, the investigators can evaluate the distance, the distance from the point where the aircraft disappeared from the radar, okay, based on, the location, GPS location at that moment, and direction, plus the velocity, okay, before it disappeared. And they would assume that they experienced a flame out. Based on that, they can track approximately the trajectory of the aircraft and where it would have landed in case they lost track of it. So this module integrates navigation theory, air traffic surveillance systems, human factors, and aircraft performance analysis. ATC recordings. ATC recordings include voice communications with the pilots, okay, like the pilot controller exchanges, radar tracks, different traces of radar for different aircrafts that would be recorded also, and data link messages, CPDLC, concerning the weather and other communications for the dew point and other weather related parameters and other parameters. Investigators in such case analyze readback, hearback errors, whether the message or the instruction given to the pilot by the ATC was understood clearly or not, clearance misunderstandings, for example, let's say the pilot suspected that or thought that he was clear to take off, meanwhile the clearance had never been given. So, a very important protocol and step was violated, or the pilot was cleared for landing or not. So let's say he wasn't cleared for landing, but yet he attempted a landing anyway. This would compromise another aircraft that's taken off from the same runway. And loss of separation events. As an example to a readback, let's say the pilot has been given an instruction such as, okay, November Mike Sierra, this is tower, XLA, fictitious tower. You are cleared to take off from runway 25 after departure. Turn right heading 150, climb and maintain 3000. Okay, so the readback would be something, repeating the same procedure almost invertly to the ATC, so as to ensure the ATC, okay, I heard you correctly, I heard you and heard the instruction accurately, so I'm going to follow through it. So the readback would be something like, climb, okay, after departure from runway 25, turning right heading 160 or 150, climbing and maintaining 3000, November Mike Sierra. Okay, so if something was wrong there, it means that he had misheard the ATC controller. Okay, So this is why it is important. Now, the loss of separation, or LOS event, is when the minimum distance required for clearance between two aircraft that are flying in the same airspace has been violated, okay? Like they came so close to each other, which can be a precarious situation that can lead to a collision mid-air, okay? Mid-air collision. So it is very important to maintain different aircraft with a clearance, a minimum clearance distance, so as to avoid them colliding against each other. Loss of separation is when you have a close call and two aircrafts come in proximity to each other, okay, which is against the rules for whatever reason. Radio signal propagation, line of sight radio range approximation is given by distance is equal to 3.57 square root of h1 plus square root of h2. Now, you might be wondering why. The line of sight between like an airport and an aircraft is like a criteria given due to the fact that the Earth is round, okay? And after a very long distance, you would have a blockage of the signal due to the curvature of the Earth. To give you a plotting for that, and this is what we're talking about. Let's say the aircraft is at a height h1, and you have like the radar here is at height h2, okay? So the distance of visibility is given by 3.57 multiplied by square root of h1. This is the first height, which is the height of the aircraft, plus square root of h2, the height of the radar itself. When that distance becomes much larger than that, the signal would be blocked by terrain, okay? And the visibility is no longer valid in such case. This is what we mean by line of sight, okay? Direct visibility between two transponders or two antennas. The first one is that of the aircraft, or like in such case, it could be the aircraft itself is acting as an antenna by reflecting the radar signal, okay? So the distance is in kilometers and h1, h2 is in meters. Now, another very important parameter in electrical communications is the signal to noise ratio, or SNR. What is SNR? SNR is basically a ratio between the power of the signal, which carries the message and like the information, the actual information, divided by the power of the noise within the signal. The power of the glitches and the noise and the different interference within the signal. So it is given by 10 log base 10 power of the signal divided by the power of noise. And by the way, when the power of the noise is very large, almost let's say it is infinity, so P over infinity of the signal gives you 0 and log 0 is 0. If the power of noise is minimal, okay, is minimal or is very, very small, that would give you one like power of signal over a very tiny value, which is almost infinity. So the signal to noise ratio would be infinity. Theoretical, I'm saying, okay? So you would have a maximum power of the signal over the noise. Blast over pressure. Peak over pressure can be approximated using TNT equivalence. The energy of TNT is given by eta, which is the efficiency factor, times mf, the mass, okay, mass of the fuel, times hc, which is the heat of combustion. So the scale distance is given by z equal r, distance from explosion, divided by equivalent mass to the power of 1/3. Overpressure determines structural failure risk and fragmentation patterns. Radar data reconstruction. Radar data reconstructs aircraft position, speed, and altitude. Primary radar range equation is given by R max is equal to PT, which is the power of transmitter, times G square, which is the gain of the antenna, okay, directive gain, times lambda square, the wavelength of the signal being used, times sigma, which is the radar cross section, divided by 4 pi to the power of 3 times S min, which is the minimum detectable signal, okay, from the effective surface of the aircraft to the power of 1 force. So this is by definition the maximum range of radar, which means the maximum distance at which the radar signal can still be detected, or it can still be reflected by an aircraft in order to detect its presence in the airspace. Okay, this is how far it can detect airplanes that are far away, located, or flying from the geolocation of the airport. Ground speed calculation, Vg is equal to delta D divided by delta T, which is the distance or change of distance being traveled from one position to another divided by time. Okay, so it is basically D1 or D2 minus D1. So distance, the second distance being traveled in reference to the first distance that had already been traveled, or to put it simply, it is the distance traveled in reference of time, okay, in reference of 2 time points, T2 minus T1. So that would give you the ground speed. Now, trajectory reconstruction uses kinematic equations. So x of t, which is the position of the aircraft at impact, you can say, is equal to x0, the original GPS location, plus vxt, which is the velocity of the aircraft, horizontal one, and usually it is considered like the same velocity. It is uniform, okay, with some alterations due to the drag of the air, okay, due to air friction multiplied by time it took for the aircraft to land on the ground. H of t, which is the altitude during each time moment, is given by h0, original altitude, original height of the aircraft, plus VZT, which is the vertical velocity, okay, the descent velocity, times multiplied by time. Radar plots are synchronized with FDR, flight data recorder, timelines. Flight planning review, investigators evaluate route selection, fuel planning, whether enough fuel was on board, alternate airports, weather considerations, and the fuel required, which is given by total fuel is equal to fuel of the trip plus fuel contingency in case something had happened, you needed extra fuel, plus fuel alternate, plus fuel that is being reserved. Okay, fuel contingency, yeah, fuel alternate is fuel for a potential alternate airport in case of an emergency landing. Okay, and fuel reserve, a reserve of fuel being on board, added to all of that. Range equation, which is the range of the aircraft, how far can an aircraft go, based on this formula. So R is given by V, which is the velocity, divided by C, or the fuel consumption, times L divided by D, which is the lift to drag ratio. How much lift versus how much drag, times Ln, which is the Neperian logarithm of Wi divided by Wf, which is the weight, initial weight of the aircraft, over or divided by the final weight right before landing. Improper fuel planning may contribute to fuel exhaustion and engines flame out in mid-flight, or diversion stress. SOP, or standard operating procedures. SOPs standardize crew actions and reduce variability. Compliance assessment includes checklist adherence, call-out discipline, briefing procedures. Okay? Error probability model. The probability of an error occurring is proportional to the ratio between deviation divided by procedural control. How much you're deviating from a procedural control would give you a probability for an error. So as much deviation happens, you would have a higher probability for a mistake. Checklist design aims to reduce cognitive load so as to reduce the strain on the pilot. Workload is given by tasks, total number of tasks, divided by the available cognitive capacity to perform these tasks. Non-compliance or normalization of deviance may indicate systemic safety issues. Automation management. Modern aircraft rely on flight management systems, FMS, and autopilot logic. Investigators would evaluate mode awareness, auto-throttle behavior, whether it was working correctly or there was a glitch in the flight computer itself due to a faulty reading, for example, from different sensors, and flight director commands. How was the flight director operating the airplane? Okay? Mode awareness, by the way, means whether the crew was aware that the autopilot was flying the aircraft, and whether they were aware of the inputs that were given by the autopilot or not. Okay? Autopilot feedback control law. UT is equal to KP ET, which is the error signal, plus KI. These are different controller gains, by the way. Integral of E of t dt, so the sum of different errors or error signals, plus KD, which is another controller gain, times the derivative of the error in respect of time. Okay, how much deviance of error is happening in respect of time. This is what it is actually pointing to. Okay, mode confusion can occur when commanded and actual flight modes diverge. Okay, so you have one program being inputted by the pilot, but you have a divergence between the pilot input and the reaction of the autopilot and the output that's being given. CFIT, or control the flight into terrain. CFIT occurs when a controllable aircraft impacts terrain unintentionally, meaning that the pilot had some control over the aircraft but did not see or was not aware for whatever reason of the terrain in front of him. So he went into a building or a mountains or a hill. Altitude error from pressure setting could be one of the reasons. So delta H, which is the differential of altitude is given by differential of pressure divided by rho g. So if the reference pressure, which is not necessarily at sea level, is incorrect, that could lead to an incorrect altimeter setting and incorrect altitude being indicated by the instrument. Incorrect altimeter setting may result in insignificant altitude deviation. Terrain clearance margin. What is the clearance? It is simply the difference between the aircraft altitude and the altitude of a terrain. This gap, this difference, gives us the clearance. How high is the aircraft from the highest point of the mountain or the terrain, or the highest obstacle such as a pole, a communication pole, or a skyscraper, etc. This is the clearance. If clearance becomes negative, it means that the aircraft can fly into terrain. That would be the CFIT, okay? And terrain impact occurs. Energy at impact would be E equal mgh, which is the potential energy, plus 1/2 mv squared, or the kinetic energy. Investigators review TAWS alerts, which is the terrain awareness alerts, approach procedures, and visibility and descent profile. Descent profile, which means how did the aircraft descend? Was the descent gradually and based on the charts, or was it abrupt, which means that something has been violated, which prevented the crew from clearing an obstacle such as a hill, for example. Okay? And visibility is very important, because if you did not have visibility, especially during the night or in cloudy environment, the crew cannot see the terrain in front of them. That could be another contributing factor. LOC-I, or loss of control in flight. LOC-I involves departure from controlled flight due to aerodynamic stall, spatial disorientation, or control system malfunction. Aerodynamic stall is when the aircraft can no longer produce lift. It might be due to the loss of both engines. Spatial disorientation, so due to a sudden, abrupt rolling motion in the aircraft. So the pilot can no longer tell whether he's flying into the terrain or whether if he's flying into the ground or pitching up into the sky. So he can no longer tell the current attitude of the aircraft. And control system malfunctions such as rudder failure, ailerons, or elevators. The stall speed again is given by Vs equals square root of 2W, which is 2 times the weight of the aircraft, divided by rho SCL max, rho being the density of the air, times S, the surface area of the wing, times CL max, which is the lift coefficient of the wing, which can vary due to different factors, especially icing. If the angle of attack exceeds critical value, that would increase the stalling speed. Okay, the lift decreases sharply, and the aircraft would stall even at high speeds. Okay, so alpha should not become greater than critical angle. Load factor in bank turn, n is equal to 1 divided by cosine phi, which is the bank angle, by the way. Higher load factor increases stall speed. So V stall is equal to V stall multiplied by the square root of n, which is 1 divided by cosine phi. Investigators analyze angle of attack data, control inputs by the pilots, stall warnings, and recovery attempts. As the final conclusion here, flight operations and ADC investigation integrates surveillance data, operational procedures, automation behavior, and performance analysis. By reconstructing trajectory, communications, and crew compliance with procedures, investigators determine whether operational, procedural, or environmental factors contributed to the accident sequence. Module 9, Aircraft Performance and Trajectory Reconstruction. Aircraft performance analysis and trajectory reconstruction are central to accident investigation. This module integrates aerodynamics, flight mechanics, and computational modeling, or simulation, in other words, to reconstruct aircraft motion and evaluate compliance with certified performance limits. Let's start with weight and balance calculations. Accurate weight and balance determine aircraft stability in mid-flight, whether like the balance or the weight was balanced means whether it was uniformly distributed from left to the right side in reference to the central cross section of or like the longitudinal axis of the aircraft, and controllability, also structural loading. Because in case the aircraft was heavier on one side, it would start a banking or a rolling motion. Okay, it would start a roll to one side, whether the right or the left, depending on where it is the heavier. Center of gravity. Here is the concept that is most important in this discussion. Okay, the center of gravity is computed using moment equilibrium. So it is the sum of different products between the weight and the distance between each weight of each component within the aircraft and the midsection. Okay, like the center, not the center, okay, the longitudinal axis that goes through the middle of the airplane. That would be the distance. Okay, so weight of each component within the aircraft times the distance from that weight point to the axis that's going in the midst or in the center of the fuselage from the tail to the cockpit, okay, divided by the overall sum of the weight. This would give you the gravitational center, okay, the center of gravity location. Wi is the individual weight, and xi is the arm or distance from reference datum. And aft CG reduces longitudinal stability, okay, in case the CG was a little bit off from the center. While a forward, okay, here we're talking about back and forth. Aft CG, which means that the center of gravity is a little bit further to the front. close to the cockpit. Okay, so it would reduce longitudinal stability, while a forward CG increases stall speed. Why? Due to higher tail download. Okay, so it would be the CG that is located before the center of the aircraft, inducing more weight to the tail section, and you would need a more like power to lift the aircraft. Okay, so this would increase the stall speed. Load factor and structural limits. Load factor is given by L, which is the lift divided by the aircraft weight. So it is the ratio between the lift force and the weight, which is the weight force. It is the force acting exactly opposite to the lift. So the lift is vertical, the weight is, both of them are vertical, I'm sorry. The lift is vertically pointed upward, but the weight is pointing downwards. So when n equal 1, the load factor is 1, okay, to the limit. Okay, now, W is the aircraft weight. So structural failure risk increases if n exceeds certified design limits. N should be much greater than 1. Otherwise, the aircraft wouldn't be able to lift in the air. Okay? Effect on stall speed. Vs nu is equal to V stall ref multiplied by the square root of the ratio between the new weight divided by the reference weight, which is the recommended weight to be carried on board, or the overall weight of the aircraft, basically. Higher weight increases stall speed, which means that the aircraft would stall even at higher airspeeds, despite the fact that in normal operations, it shouldn't stall until it decelerates, until it attains, let's say, during landing, less than 165 knots, okay? But when you have higher weights, this apply more load to the aircraft, countering the lift power, so the lift would be degraded even at higher speeds. This would increase the stalling speed. And of course, it would directly affect takeoff and landing margins. Takeoff and landing performance. Performance calculations determine whether the aircraft met required runway margins. So here we measure the takeoff ground row, which is the distance required for an aircraft to become airborne, to actually lift off from the runway. Using work energy principle, S, which is the ground row distance, is given by V squared divided by 2A. Okay? V is the liftoff speed and A is the net acceleration. So, acceleration depends on the formula A equal T thrust minus drag, okay, T minus D minus mu, which is the dynamic viscosity, times weight minus lift, divided by M, which is the mass of the aircraft. Now, to explain a little bit, where did this formula come from? Okay, based on the work energy principle. Okay, so you have the work is given by force multiplied by distance, which is the force, as we know, based on the second law of Newton, is M times A. Okay, so the work is equal to F, the force times distance, which is S in this case, equal MA times S. This is equal to the kinetic energy, okay? So this becomes a kinetic energy, which is 1/2 mv squared. So m is reducted from both sides. It is it is eliminated. It cancels out. So what remains is S is equal to 1/2a times v squared equal, so basically, S is equal to v squared divided by 2a. This is where we got this equation from. Balanced field length. Balanced field condition occurs when distance of acceleration minus the go distance is equal to distance of acceleration minus the stopping distance. So in other words, at V1, and this ensures safe decision at V1, which is the velocity, after which you can no longer abort the takeoff in case you had an emergency on board. So whatever problem that you have, you would need to take it airborne with you and solve it in the air. However, if there was a problem that had been detected prior to V1, you can still abort the landing while guaranteeing enough stopping distance without offshooting the runway or running into an obstacle at the end. Okay? So the S accelerate minus go distance is equal to S accelerate minus the stopping distance. You still have enough stopping distance before, endangering the aircraft. Landing distance. Braking deceleration is given by A equal mu times G, mu being the dynamic viscosity times G, which is the gravitational acceleration. Landing roll, which means how much distance or how much runway the airplane would eat up once it lands. It is a factor that has to do with the touchdown speed and the dynamic viscosity, actually the friction coefficient of the runway. That is mu. Okay, so S is equal to V squared TD, which is the touchdown speed, divided by 2 mu G. 2 times mu, which is the runway friction coefficient, multiplied by G, which is the gravitational acceleration. Contaminated runways significantly reduce mu, which is the friction coefficient. Here, in this context, when we talk about contamination, we would be referring to factors such as ice on the runway or snow on the runway, okay? That would cause a skidding motion with the airplane. Climb gradient assessment. Climb performance is essential for obstacle clearance. The rate of climb, or ROC, is given by T, which is the thrust, minus D, or drag, multiplied by velocity, divided by the weight of the aircraft. This is what will determine the climb rate. Climb gradient is given by ROC divided by V, which is the rate of climb divided by velocity, equal T minus D divided by W. Thrust minus drag divided by weight. Regulatory minimums imply that a minimum of 0.024 or 2.4% for twin-engine transport aircraft are evaluated against reconstructed data. Energy state reconstruction. So total mechanical energy determines aircraft maneuverable capability. Total energy is equal to potential energy plus kinetic energy, or mgh plus 1/2 mv squared. Specific energy per unit mass is equal to ES equal GH plus V squared over 2, where M is infinitely small or unitary. Energy rate is ES equal GH plus VV, okay? That would be the rate of energy. Investigators assess whether the aircraft had sufficient energy to avoid terrain or stall. Glide performance is given by the ratio between L and D, which is glide distance divided by altitude loss. Maximum glide range occurs at maximum L over D ratio. So how much gliding distance the aircraft is traveling while losing minimum altitude, because both of them will happen at the same time. Flight path modeling software, trajectory reconstruction, integrates recorded parameters of FDR, ADS-B into dynamic models and simulators based on Newtonian mechanics and Newton's second law of motion, which is sigma F is equal to ma. Sum of all forces is equal to the mass of the object multiplied by the acceleration. In three-dimensional space, m dv over dt is equal to t plus L plus d plus w. Basically, dv over dt is the rate of change of velocity in terms of time, or the derivative of velocity in terms of time. In other words, the acceleration, A equal dv over dt. So this is sigma F equal ma. Sigma F to the right this time is the sum of different forces acting against, it is the vectorial sum, by the way, of different forces acting against the aircraft. So T is the thrust plus lift plus drag plus weight. Okay? Numerical integration techniques, e.g. Runge-Kutta methods, solve differential equations to reconstruct position and velocity. Now, position is the integral of vt dt, okay, of different velocities multiplied by their time spans. Outputs include ground track, vertical profile, angle of attack history, and load factor variation due to wind loading. Now let us draw a small diagram to visualize the different forces acting against the aircraft. Let's say this is the aircraft, okay? This box here represents the aircraft. So lift force is in this direction. The weight is the one acting against it. And by the way, I'm considering here a leveled flight because when you have a roll, things will definitely change, okay? Then you have the thrust, which is the force acting forward against the airplane being generated by the engines, and the drag, which is the air opposing the forward motion of the aircraft, okay? So these are different forces mentioned here. 6. Simulation tools. Simulation tools validate hypotheses through controlled parameter variation. Okay, so we're going to talk at first about Monte Carlo analysis used to evaluate uncertainty. Okay, it is called, measuring the shortest road or the shortest path in order to get into to get to an outcome or a conclusion. So basically, it is a statistical method in order to get an assessment of a certainty, or usually used to measure the shortest path to get from point A to point B among different paths, different criteria in this case. So Px, probability of any event, is equal to the number of favorable outcomes divided by total simulations. Okay? Sensitivity analysis, if output variable y depends on parameter x, so sensitivity is given by delta y, or divergence of y, the change of y variable in term or in respect of the change of x, okay? Just like when you derivate velocity in terms of time. High sensitivity indicates critical investigation focus. Now to give an example and a refreshing concerning the probability and how we measure probabilities. Let's say you have a bucket with, let's say, 5 balls, okay? One of them is solid red and the other balls are white, okay? So what is the probability? The probability when someone draws one ball to get that red ball instead of the other 4. That would be given by number of favorable outcomes. In this case, one favorable outcome, which is drawing this ball, okay? No other ball, because we don't have 2 red balls. In case we had 2, you would have 2 favorable outcomes, either drawing the first one or the second one. So it is 1 divided by the total number of simulations, which is, you can draw this one, this one, this one, this one, or this one, which means here in this context, the total number of balls, which is 5. So that would be 1 divided by 5, or 20%. 0.2 or 20% probability of drawing the red ball. Real-time flight simulators. Certified full flight simulators replicate aerodynamic models. So you have CL, lift coefficient, is equal to CL0 plus CL0 alpha, which is the parameter or like the bias that you would input in order to simulate, for example, icing on the wings. The drag is given by 1/2 rho v squared dynamic pressure times S surface times the drag coefficient. That can also change based on the angle of attack and other factors. Also, icing can contribute to drag, increasing the drag coefficient while degrading the lift coefficient. These models test pilot inputs, system failures, and environmental factors to compare simulated data, simulated behavior of the aircraft with recorded data of the crash in order to make sure and validate the proposition or like the assumption of what had happened based on different researches to draw a final conclusion of what truly had taken place. Conclusion. Aircraft performance and trajectory reconstruction combined physics, engineering, and computational fluid dynamics, and computational modeling as well, to determine whether the aircraft met certified performance margins, if weight and balance contributed to instability, whether sufficient climb gradient existed, if energy state allowed recovery, whether trajectory aligns with aerodynamic laws. By integrating aerodynamic equations, energy analysis, and advanced simulation tools, investigators transform raw data into scientifically validated conclusions regarding aircraft motion and performance limitations. Module 10, Fire, Explosion, and Security-Related Events. Fire and explosion events in aviation involve thermodynamics, combustion chemistry, structural mechanics, and forensic science. This module analyzes ignition mechanisms, flame propagation within the airframe, blast effects, and coordinated investigative procedures. Fuel air explosion dynamics. Fuel air explosions occur when vaporized fuel mixes with air within flammability limits and is ignited. Flammability limits. Combustion occurs only when the fuel-air ratio lies between the lower flammability limit, LFL, and UFL or upper flammability limit, where phi is the equivalence ratio given by F over A actual divided by FA stoichiometric. Combustion energy release. Heat release from combustion is given by Q equal mf times HT, where mf is the mass of the fuel, multiplied by heat of combustion. Categories of deferral. A, as specified in MEL. B, typically 3 days deferred, not more. C, typically 10 days. And D, it could be done in 120 days. Risk implications. Deferred fire detection systems, inoperative cargo compartment sensors, or 40 APU fire bottles may significantly increase risk. Operational risk can be conceptualized as risk is equal to the probability of a failure multiplied by the consequence of the failure. Cabin fire propagation. Cabin fires involve heat transfer, material flammability, and smoke dynamics. Heat transfer mechanisms. Total heat transfer, Q, is given by Q conduction, conduction transfer plus Q convection, plus Q radiation, temperature being radiated. Okay? Conduction, which is by direct contact. Okay. So, conduction is given by Q equal minus K A times dt over dx, with K being the thickness of the material, which is usually the metal, multiplied by A, or area of exposure to heat and temperature, times the differential of temperature in terms of distance. So let's say the temperature had increased by 20 degrees in 1 centimeter. That would be dt over dx. And radiation, which is Q, is equal. So conduction through radiation is given by, heat transfer through radiation equal sigma, which is, by the way, this is the relationship of Stefan-Boltzmann. Sigma is the Stefan-Boltzmann constant multiplied by epsilon, which is the permittivity, times A, the area, multiplied by T, which is the temperature in Kelvin to the power of 4. Fire growth rate for many cabin materials, Qt, which is the fire growth rate, is given by alpha times T square. T is the time factor, and alpha is the fire growth coefficient. Okay? So rapid growth can lead to flashover when surface temperatures exceed ignition thresholds. Okay? So it would be spilling over other materials as well, like crossing barriers. Smoke layer descent, which is the smoke descent velocity, relates to buoyancy driven flow. It is given by, actually it is directly proportional to the square root of g, acceleration of gravity, multiplied by h, which is the heat, times delta t over t, which is the temperature difference divided by the temperature of the ambience, okay, of the environment. Toxicity assessment involves CO concentration and exposure time. Lithium battery fires. Lithium-ion batteries pose unique risks due to thermal runaway. Thermal runaway condition. Okay, here you have the heat balance is given by M, which is the mass of lithium within the batteries, the inflammable components, times Cp, which is the calorific capacity, multiplied by dt over dt, which is the thermal runaway, the thermal shift in terms of time, is equal to Q generation, okay, the heat generation minus the heat loss, okay? Thermal, not the heat, the heat transmitted source, to speak, okay? The heat energy generated minus the heat energy loss. Thermal runaway occurs when Q generated is greater than Q loss. So you have an overheat leading to a fire. So again, Q is the heat transfer, okay? So when the heat transfer becomes greater than the heat that is being lost during the transmittance, during the conduction, this is when thermal runaway occurs, which means that the heat would be transferred over to other places and causing an incendiary phenomena, okay? But when this overheat is being lost, okay, within different parts of the airframe without being transmitted, and I'm talking about the barriers that are not flammable, it would not cause a fire, all right? Internal short circuit heating. Electrical power is given by Ri squared. I equals short circuit current. In case of a short circuit, you would refer to I as being the current of short circuit, okay? Square multiplied by R. So high temperatures decompose electrolyte and release flammable gases. Gas venting pressure, ideal gas approximation, PV equal nRT. Rapid gas generation increases internal pressure, leading to rupture or explosion. Okay? Why? Due to the fact that the rise of the pressure can be affected by the temperature. So when you have an increase in temperature, you have an expansion that could lead to a depressurization or an explosion. Okay? Rapid gas generation or an increase in volume in such case increases internal pressure, leading to rupture of the airframe or explosion. Mainly, it can be either the temperature rising through a compartment or whatever, or a rise in the volume itself that would increase the pressure, and this would place more stress against the airframe. Sabotage and unlawful interference. Security-related events such as a bomb going off on board require multidisciplinary forensic analysis. Okay? So you would need to examine in such case explosive residue through analyzing the residues of of the crash of different fragments and debris. Now, the detonation velocity, by the way, is given by D equal square root of 2E, which is the explosive energy, divided by the mass of explosion. Fragment velocity estimation, the velocity of the fragment after the explosion, is given by square root of 2E divided by mass of the fragment. Okay, that would be the velocity after the explosion of the fragment itself. By the way, in case you are still wondering, this is derived from the kinetic energy formula. So let me sketch it a little bit. In this case, the velocity being d instead of v. So E is equal to 1/2 md square. So d is equal square root of 2e, you see here, divided by m. This is what we're talking about. Structural failure from blast load. Impulse momentum relationship is given by I equal to integral or sum of force multiplied by time, which is basically m delta v or mass, times the differential of velocity. Okay? So blast impulse helps determine whether structural breakout occurred or started in flight or upon impact, which is a very important cue on the investigation, so as to explain where the problem had started, or whether it was a structural breakup in midair, or the breakup is basically due to the forces of impact. Security chain of custody. Evidence handling follows documented continuity to ensure admissibility and prevent contamination. To give you a clearer picture and a clearer explanation over this formula and what it means actually, this is the overall sum of forces acting against wreckage and the total effect of these forces in terms of time. Okay, so as the force persists while pushing a debris or like a fragment in a specific amount of time, the total effect is being measured, okay, of that force acting on that wreckage, acting on that dismantled or broken object, okay, that had separated from the airplane. This is exactly what we're evaluating. Now, where it comes from, you see, F is equal to ma, mass times acceleration. This is second law of Newton. And A is equal to delta V over delta T, which is the rate of change of velocity in terms of time. Okay, so you have m delta V over delta T or dt. Okay, so basically F is equal to m delta V over delta T, correct? So delta T or dt, you multiply it back with F and you integrate. So integral of F times dt is equal to m delta V. This is where it came from. And this is called the impulse, which is again, is the overall effect of a force acting against an object through a span or like during a specific span of time. Forensic evidence coordination. Accident scenes require coordinated technical and legal processes. Okay, starting from fragment trajectory reconstruction, so projectile motion model is given by these formulas, which is x is equal to v0 cosine theta t, theta being the angle of the motion of the aircraft between like the velocity vector of the aircraft and the horizon, which is the reference plane parallel to the ground, so to speak. Okay, v0 is the original velocity upon loss of engine power, let's say, or loss of controllability, multiplied by time, and you have the other formula is y is equal to v0 sine theta t, also v0 being the original velocity, theta the angle right before like the aircraft started going down, times t, minus 1/2 gt squared, g being the gravitational acceleration. From that, you can draw, like from the distance and altitude, you can draw how long it took for the aircraft to hit the ground. Or if we can get t here, okay, you can replace it in the first equation and learning the actual distance traveled before impact. Okay, it is used to estimate in-flight breakup altitude as well. Okay, depending on what parameters you have, you can get the others based on these formulas. To give you an example, so let's say you have the altitude was, let's say, 1000, V0, whatever. Okay, I'm gonna add fictitious values, so it is 5t minus t square. Okay, so t square minus 5t plus 1000 equal to 0. You need to use the discriminant in order to find, okay, delta, which is b squared minus 4 ac, b being this factor here, and ac is what is multiplied by t squared, which is 1, times c, which is 1000. Okay? Now, after getting delta, you would get two values for t. The first one being 0. I'm sorry. Okay. The first one being based on the evaluation. Okay. Minus b, which is plus 5 in this case, minus square delta over 2a. 2 times a, this is a. Okay. Because the format of the formula or the equation is 80 squared plus bt plus c is equal to 0. Okay. This is a quadratic equation of this form. Okay. And the equation is here, t squared minus 5t plus 1000 is equal to 0. So c is 1000, b is minus 5, and t is 1. Okay? So t1 is minus b minus square root of delta divided by 2a. t2 is plus b plus square root of delta divided by 2a. Okay? You get the time, then you replace it in the first equation. You can get the maximum distance traveled before impact. Metallurgical analysis. Stress at failure is given by sigma is equal to F divided by A. So it is the division between the force over the area where the force is acting. Fracture mechanics parameter, which is K, Ki, is given by Y, which is the geometry factor changing from one geometry type to another, multiplied by sigma, which is the stress, times square root of pi a, where a is the crack length, or the length of the crack. Comparison with material toughness, KIC determines failure mode. Evidence correlation. Time synchronization between FDR or flight data recorder, CVR or cockpit voice recorder, which records different conversations and different sounds heard in the cockpit, ATC radar data, which tracks the trajectories of different aircrafts all the way to their destination, and wreckage distribution. All of that can collaborate and contribute into deciphering what happened prior to the accident. Temporal correlation is needed, which supports causal sequencing of fire, explosion, or security events. Conclusion. Fire, explosion, and security-related aviation events require integration of combustion thermodynamics, so you have multiple sciences working together here, blast wave physics, or propagation of shock wave, heat transfer modeling, electrochemical failure analysis, so failure when it comes to chemistry and the mixture of chemistry and electricity, or fire science, so to speak, and forensic structural mechanics. Through quantitative modeling and coordinated forensic procedures, investigators determine ignition source, propagation mechanisms, structural response to the fire or combustion or explosion or other events, and potential unlawful interference, forming scientifically defensible conclusions. Module 11, Maintenance and Organizational Factors. Maintenance documentation analysis. Maintenance documentation analysis is a critical component in investigating fire and explosion-related accidents. Proper documentation ensures traceability of inspections, repairs, part replacements, and compliance with regulatory requirements, which is necessary in order to track back different operations of maintenance done on the aircraft, such as part replacement, a maintenance procedure, and how it was undertaken, whether, if it had followed the regulations or not, which is necessary in order to trace back what had happened and why. The causality of the accident and the breaking apart of the airplane. Key elements: aircraft technical log or ATL, work orders and task cards, airworthiness directives or ADs, service bulletins when you have something that needed to be adjusted or rechecked, or this is given as a service bulletin as an improvement on a specific maintenance procedure. Component history records, which means what had happened before when it comes to a component. Let's say it had a chronic failure symptom and it was fixed over and over, but never actually been fixed, okay, been dealt with. And non-routine defect reports. So defects that are non-routine and unusual, or in other words, it should have been like repaired in a better way, or a part should have been replaced, but yet they chose to plaster over it or to fix it outside of regulatory norms. Investigative focus. Investigators assess whether maintenance was performed in accordance with approved data, whether fire detection / suppression systems were inspected at required intervals, if recurring defects were properly addressed also and were maintained based on the norms and regulations, and the maintenance procedure that is proper for that type of aircraft, and whether documentation gaps indicate procedural deviations. Deviation means that it should be done this way, but there was some compromise or cutting corners. Reliability and failure tracking. Maintenance trend analysis often uses reliability metrics such as failure rate. Lambda, which is the failure rate, is the ratio between NF, or the number of failures observed, divided by the total operating time. For constant failure rate systems, the reliability is R of t is equal to exponential minus lambda t. This is particularly relevant when investigating repeated fire warning faults or electrical arcing events. Okay? Now, deferred defects, or MEL, the minimum equipment list MEL approved under regulatory frameworks such as those of the FAA, Federal Aviation Authorization or Administration, or the EUA, okay, EASA, or European Union Aviation Safety Agency, permits certain defects to be deferred, to be postponed under controlled conditions. Where P of failure may increase due to deferred corrective action, C, the consequence in fire explosion scenarios, is typically catastrophic, and repeated deferrals may increase cumulative system risk. So P, cumulative risk, is equal to 1 minus the sum of 1 minus PI, where PI is the probability of failure, okay? That would be the cumulative probability of risk becoming very dangerous. This formula becomes relevant when multiple related systems are deferred simultaneously, which would increase the amount of risk. Quality control failures, or QC, ensures that maintenance activities meet airworthiness standards. Airworthiness means if the aircraft is flyable or not. Failures in QC or quality control can lead to improper installation, wiring errors, fuel leaks, or compromised fire barriers. This will mean here that the fire would propagate much faster due to the failure, or the lack of installments when it comes to barriers, or the barriers that are supposed to block the fire have been installed improperly, okay, outside of the norms. Common QC breakdown areas: inadequate independent inspection, tool control lapses, FOD risk. So you would have, for example, something forgotten within the aircraft, within a compartment of maintenance, that would become a flying object that incurs damage due to motion. Improper torque application against the bolt, which would cause a crack in the bolt and a failure in the future, because that crack would start developing. Incorrect part installation, so installing one part instead of the other, correct? Like it happened in one of the flights. It was, I think, an ATR 72, Algerian Airlines, and they replaced one, I'm not sure if it was the fuel, the fuel counter, the fuel measuring gauge, okay? So that instrument was replaced by another one belonging to the same ATR but from a different version. So the sensor brought down different calculations, so the measurement of the fuel was completely false. it gave like the pilots the illusion that the tanks were full, but in fact the tanks were completely empty. Okay, so improper torque application, incorrect part installation, and poor documentation verification. Swiss cheese representation of QC or quality control failure. Accident probability increases when multiple layers of defense fail altogether. So the probability of the accident is given by the sum of different probabilities for different barriers, such as the maintenance, following the documentation, that would be the barrier. Another barrier is securely like installing some of the equipment or instruments securely and properly fastening the boats without applying more torque. Actually, even lesser torque can be dangerous. Why? Because the boats might loosen due to excessive vibration that is caused by the airflow, okay, as the aircraft is flying through the air and by wake turbulence, for instance. Okay, so these different deviations can sum up and they can lead to a cumulative error, okay, problem, eventually ending with an accident. Okay, with an accident taking place where each P barrier failure represents a failed safety defense. Okay, for example, inspection, supervision, audit, etc. SMS or safety management systems. A safety management system, SMS, is a structured framework mandated by authorities such as the ICAO for managing operational safety risks. 4 pillars of SMS. First of all, safety policy, safety risk management, safety assurance, and safety promotion. Risk assessment within SMS. Risk matrices evaluate severity and likelihood. So the risk index is given by S, which is the severity level, multiplied by the likelihood of something happening, okay, which is L. In fire explosion events, severity is often classified as catastrophic in such case, because fire, okay, the fire can consume the entire aircraft, asphyxiate the entire cabin, rob the cabin from oxygen, the pilots and the crew, and even the passengers, plus destroy structurally different parts of the aircraft. Not to mention, the probability of an explosion also, okay? So, and losing control surfaces. Even low likelihood events require mitigation due to high severity. Organizational accident causation models. Organizational accident models explain how systemic or systematic failures contribute to catastrophic outcomes. Okay, Reason's Swiss cheese model. So it was developed by James Reason. That's the name of the one who came up with the Swiss cheese model. This model conceptualizes defenses as layered barriers with latent weakness. Okay, so the accident is equal to latent conditions plus active failures. Okay, some of that. Latent conditions include inadequate training of the pilots, budget constraints, which made the maintenance crew cutting corners, for example, replacing a boat with another one that is not based on the norms. So you are deviating from the protocols of maintenance and the design documentation of the aircraft itself. Okay, because narrow boats can withstand lesser shear stress. They would break eventually, okay, after developing cracks. And weak oversight, which means weak sight over the distance concerning what would be the consequences of different actions that had deviated from the regulations. Active failures include maintenance error, procedural violation, and misinterpretation of warning indications. Now, when we talk about maintenance error, that would have to do with a mistake being made. So instead of following a specific procedure, another procedure that was more fitting for another type of aircraft was followed, or a replacement of one part by another, thinking that would be actually in such case a procedural violation, a deviation from the regulations, okay? Or a specific compromise due to the fact that we don't have this part, so this one would work, although it is not the specific part, it's not the exact one, and it is outside of, like, it's not compliant with the regulations and with the different characteristics of what should have been done and the parts that should have been installed as a replacement to the worn out parts. Okay, so third, misinterpretation of warning indications. So the pilot or the crew would get a warning and misinterpret it as being indicating like fuel leak or a flame out or whatever, due to like a sudden lurch of the airplane or a startle effect. So this is in mid-flight, but when we're talking about ground operations, it would be a warning sign from an instrument being interpreted as something else, completely different than what it is, okay? Like a false retard alarm or a false engine indication, etc. Many possibilities here. And again, when it comes to maintenance error, it would be following a different procedure than the correct one. And due to, you know, the need to push the deadline, or like to push the aircraft to the runway so as to catch up to a schedule, these errors would occur. HFACS, or Human Factors Analysis and Classification System. HFACS expands causation into 4 levels: unsafe acts, preconditions for unsafe acts, like for example, the lack of training for the maintenance crew or for the in-flight crew. Third, organizational influences, so the pressure to perform, the pressure to finish the job, or like finish the maintenance of different airplanes on time, okay, even while compromising specific safety measures that should have been taken. Systemic accident probability may be conceptualized as PA is equal to F, a function of OSPU, which is organizational influences, supervision, preconditions, and finally unsafe acts. Application to fire and explosion investigations. Organizational causation often underlies improper fuel tank maintenance, wiring inspection intervals extended beyond safe margins, so the wires, the electrical wires, worn out and they started surging and arcing. Okay, you would have discharge in the air or electrical sparks going off between the different polarities of the electricity, the positively charged wire versus the negatively charged, or the insulation wearing out and overheating of the insulation. And normalization of deviance in fire warning system deferrals, so they would push ahead some of the maintenance necessary to be done, okay, they would start pushing them ahead, okay, from one schedule to another, which is very dangerous. Understanding systemic interaction is essential because catastrophic fire events rarely result from a single technical failure, but rather from a layered organizational breakdown or breakdowns having been accumulated for a relatively longer period of time. This is what causes different problems to escalate into a full-blown fire. At the end, thank you so much for watching, and I hope that you enjoyed this video.